X-ray emitting plasma interacts with the giant elliptical, influencing its and that of its satellite galaxies. Gas stripped from smaller neighbor pressure interactions enriches the medium, contributing to the overall complexity of the system. These processes highlight the dynamic nature of galaxy clusters, where gravitational forces and high-energy phenomena shape the universe on vast scales. Beyond its scientific significance, this cosmic monarch serves as a reminder of the diversity and scale of the universe. Its immense size, brilliance, and section within the Abell 2029 cluster make it a prominent cosmic landmark, a beacon of light visible across hundreds of millions of light-years. This galactic titan provides a glimpse into the distant past, offering insights into the intricate interplay of forces that have shaped the cosmos. As research progresses, this ancient Galaxies and its analogues will remain pivotal to our quest for understanding the universe, offering a window into its boundless possibilities. The giant elliptical of Abell 2029 continues to intrigue astronomers with its sheer scale and complex history. This celestial titan, alternatively called the Abell 2029 core galaxy, stands as a testament to the immense forces at play in the universe. Measuring over 6 million light-years across, it dominates its star in both size and influence, earning titles such as the Colossus of Virgo in astronomical discussions. This supergiant has undergone countless mergers, consuming smaller galaxies in a process that has shaped its current structure. Each interaction has added stars and gas, further enriching the galactic core. This relentless process, known as galactic cannibalism, underscores the dynamic interactions within dense cosmic environments. At its heart lies a supermassive black hole of extraordinary proportions, sometimes referred to as the gravitational anchor of Abell 2029. With a mass surpassing 40 billion suns, it is among the largest ever detected, governing the motions of stars and gas within the galaxy, while exerting influence on the broader cluster environment. The intense gravitational field of this singularity contributes to the luminous core, radiating across vast distances, earning it epithets such as the light beacon of Virgo. The stellar population of this ancient Galaxies is predominantly old and yellowish, characteristic of elliptical galaxies. Most stars within this vast system exceed 10 billion years in age, marking a galaxy that has long since exhausted its supply of cold gas necessary for star formation. Instead, the yard of Abell 2029 glows faintly with a golden hue, a visual indicator of its advanced evolutionary stage. Surrounding this interstellar monarch is a vast dark matter and interstellar material, or the cosmic veil of Abell 2029, extending far beyond its visible boundaries. This halo influences the cluster's gravitational dynamics. Within it, intracluster light, a faint glow from stars stripped from their original galaxies, adds an ethereal quality to the region. These orphan stars, drifting through the intergalactic sea, serve as evidence of the violent history of galactic interactions that have defined the Abell 2029 monarch. The surrounding environment of this galactic elder is rich with X-ray emissions, a consequence of the hot plasma filling the Abell 2029 cluster. These high-energy phenomena, observable by Chandra and XMM Newton, reveal the turbulent conditions within the X-ray furnace of this dense system. Interactions with the cluster's tidal forces strip gas from smaller galaxies, enriching the intracluster medium and fueling the ongoing evolution of this cosmic giant. Studying this luminous elder of the universe provides unparalleled insights into galaxy formation and evolution. As one of the largest known galactic structures, it serves as a crucial subject for exploring extreme cosmic phenomena. The role of supermassive black holes, dark matter, and galactic mergers in shaping such immense systems remains a fundamental question in astrophysics, with the Colossus of Abell 2029 offering valuable clues. Despite its age and apparent dormancy in star formation, this golden leviathan continues to exert significant influence on its surroundings. Its gravitational pull dictates the movements of satellite galaxies and contributes to the broader dynamics of the Abell 2029 cluster. As the gravitational heart of Virgo, this celestial giant exemplifies the scale and power of cosmic structures, a reminder of the vast forces governing the universe. This eternal sentinel of the Virgo supercluster, sometimes referred to as the cosmic giant, stands as a silent witness to nearly the entire history of the universe. With an unfathomable size, this ancient behemoth has absorbed and consumed countless smaller galaxies, preserving a vast record of cosmic evolution within its structure. At its core lies a supermassive black hole of unimaginable scale, often described as the Abyssal King or the Dark Heart of Abell 2029. With a mass exceeding 40 billion suns, its gravitational pull is so intense that even light struggles to escape. The energy released by matter spiraling into this behemoth generates a luminous halo of X-rays, an eerie beacon that signals its presence across intergalactic space. This singularity, the cosmic anchor, dictates the structure of its host galaxy, binding stars and dark matter in an unending gravitational dance. The luminous behemoth stands as a monument to galactic cannibalism, a relentless cosmic predator. Over billions of years, it has consumed not just a few, but potentially thousands of smaller galaxies, merging their stars, gas, and dark matter into its sprawling form. These ancient collisions, some violent and others gradual, have left imprints across its vast halo, a graveyard of shattered galactic identities. Each merger has been a step toward its immense scale, making it one of the largest galaxies ever observed. Often described as the universal apex, it represents the ultimate fate of many evolving galaxies. Despite its outward stillness, this silent monarch is far from dormant. While its visible light radiates a golden hue, a testament to its aging stellar population, its hidden layers remain active. X-ray telescopes reveal a sea of hot plasma permeating the intracluster medium, a cauldron of gas stripped from neighboring galaxies via gravitational interactions. This invisible fire glows in high-energy wavelengths, exposing the turbulent forces shaping the Abell 2029 cluster. The galaxy's cosmic shroud, an immense halo extending beyond its core, envelops countless orphaned stars. These unbound celestial wanderers drift aimlessly through the cluster, their faint collective glow known as intracluster light, preserving the story of ancient galactic violence and ongoing cosmic evolution. Here, in the interplay of light and shadow, lie countless mergers, some unfolding over millions of years, others in cataclysmic bursts. Yet, it is not only its scale that makes this stellar colossus remarkable, it challenges fundamental understandings of the universe itself. How did such a massive structure form? What are the limits of galactic growth? These unanswered questions push astronomers to look deeper into the void, searching for clues within the glow of this cosmic elder. Its existence serves as a reminder that, despite its apparent stillness, the universe is an ever-evolving place of energy, motion, and transformation. The role of dark matter in shaping this cosmic sovereign cannot be overstated. Without this enigmatic, unseen force, its vast mass would not remain intact. Scientists theorize that this dark empire of the cosmos is encased in a titanic dark matter halo, stretching far beyond its luminous boundaries. This invisible structure not only binds its stars together, but also dictates the motion of galaxies within the Abell 2029 cluster. Studying dark matter in such a monumental system provides essential insights into the forces that govern the universe on the largest scales. Perhaps most hauntingly, this eternal giant offers a glimpse into the ultimate fate of galaxies like our own. Over billions of years, as galaxies collide and merge, they gradually lose their distinct forms, their spirals fading into smooth, featureless ellipses filled with aging stars. In this way, the timeless Leviathan serves as a harbinger of cosmic inevitability, offering a vision of what the Milky Way and its neighbors may one day become. Yet, despite its dominance, Even this galactic juggernaut is not eternal. The universe's expansion will eventually isolate it, as neighboring galaxies recede beyond the observable horizon. Trapped in an ever-growing void, this universal colossus will gradually dim, its stars burning out, leaving behind a cold, dark remnant. But for now, it remains a beacon of knowledge, a living relic of the universe's tumultuous past, the ancient monarch of Abell 2029, one of the grandest elliptical galaxies ever discovered, is more than a single entity. It is a microcosm of cosmic history. Every star within its vast expanse, every faint whisper of gas, every drifting shadow of dark matter holds a story spanning billions of years. This stellar labyrinth challenges our perceptions of time and space, inviting us to unravel its secrets, while reminding us of the universe's boundless complexity. The sheer magnitude of this galactic behemoth, sometimes called the infinite tapestry of Virgo, places it in a class of its own. Spanning over 6 million light-years in diameter, it could only have formed in one of the densest and oldest galactic the Abell 2029 cluster, a gravitational cauldron housing thousands of galaxies, provided the ideal conditions for such a titan to emerge, often referred to as the cosmic overlord. This dominant force that sculpts the motions of stars, gas, and galaxies across millions of light-years. At its center lies its most mysterious and formidable feature, a supermassive black hole of unimaginable scale, sometimes called the cosmic abyss. This gravitational leviathan is not merely a point of intense mass, it is a dynamic engine, consuming and unleashing vast amounts of energy through radiation and relativistic jets. These jets, stretching for hundreds of thousands of light-years, act as cosmic lighthouses, visible across intergalactic distances. They also reshape the surrounding environment, heating nearby gas and preventing it from cooling into new stars. The intricate relationship between this dark heart and its host galaxy is one of the many puzzles astronomers seek to unravel. The Virgo Colossus, with its ancient history and staggering scale, continues to intrigue scientists, offering a glimpse into the most extreme conditions the cosmos can produce. Every observation of this celestial titan deepens our understanding of the vast and evolving universe, reinforcing its place as one of the greatest galactic wonders ever discovered. This galaxy, sometimes poetically called the eternal jewel of the universe, stands for a bygone era, a testament to the cycle of galactic life and death across cosmic timescales. Its stars, predominantly ancient, resemble the dim embers of once bright stellar populations, collectively known as the Golden Veil of Abell 2029. These aging stars give the system its characteristic yellowish hue. The absence of young, blue stars confirms that star formation within this stellar mausoleum ceased long ago, leaving behind a tranquil celestial giant. Yet, for all its apparent serenity, this universal titan bears visible scars of its violent past. Faint trails of intracluster light, drifting remnants of past galactic collisions, surround it like ghost galaxies. Often stars, stripped from their now drift aimlessly in the gravitational tides of the cluster. Observing this cosmic haze allows astronomers to reconstruct the history of mergers that have fed this stellar behemoth over billions of years. Each dim glow represents more than just a star, it is a lost galaxy, long since absorbed into the greater whole. The surrounding environment, often called the fiery realm of Abell 2029, is a place of extreme conditions. The intracluster medium, a searing plasma heated to tens of millions of degrees, fills the space between galaxies. This inferno is a direct result of gravitational energy released during galactic interactions, as smaller systems are drawn into the gravitational throne of the cluster's core. Their gas is stripped away, enriching the scorching medium. These not only the cluster's fate, but also the continued evolution of this cosmic monarch. The story of this interstellar giant unfolds across the entire electromagnetic spectrum, reveal vast lobes of relativistic particles, remnants of past outbursts from its central black hole. Infrared surveys uncover traces of dust-silent echoes of an era when star formation was still possible. Every wavelength of light paints a different portrait, offering astronomers a multifaceted view of this infinite expanse of Abell 2029. Yet, the greatest mystery of this silent king of clusters lies in what cannot be seen: dark matter. The invisible substance that dominates the universe's mass plays a fundamental role in its structure. Without an immense dark matter halo encasing this stellar leviathan, its gravitational influence could not hold such a sprawling structure. Together, this invisible crown extends well beyond the galaxy's visible boundaries, binding not only its stars, but also anchoring the entire Abell 2029 cluster. The timeless Galaxies is more than just a relic, it is a symbol of the universe's relentless expansion. As space itself stretches, galaxies grow more isolated. One day, far in the future, the Abell 2029 cluster will drift so far from its cosmic neighbors that it will become an island of light in an otherwise unreachable void. The stellar empire will remain, but its surroundings will fade into darkness, a sobering reminder of the inexorable forces shaping the cosmos. Yet, in form, the eternal beacon of Virgo continues to shine, offering humanity a glimpse into the ultimate limits of galactic evolution. It stands as both a challenge and an inspiration, a cosmic enigma urging astronomers to push the boundaries of knowledge. Each discovery brings us closer to unraveling the mysteries of this cosmic colossus, deepening our understanding of the largest and most ancient structures in the universe. The primordial sovereign of Abell 2029, sometimes called the cosmic monarch of Virgo, is not merely a passive relic, it is a living record of the universe's history. Every star in its vast expanse, every whisper of gas, and every drifting shadow of dark matter tells a story spanning billions of years. This stellar labyrinth challenges our perceptions of time and space, inviting us to decipher its secrets and reminding us of the infinite complexity of the cosmos. The sheer size of this galactic behemoth, sometimes described as the infinite tapestry of Virgo, places it in a category of its own. Spanning over 6 million light-years, it exists only in the densest and most ancient galactic environments. The Abell 2029 cluster, a gravitational cauldron of thousands of galaxies, provided the perfect conditions for such a titan to emerge. At the heart of this vast system, the cosmic overlord dominates its region, its gravity shaping the motions of galaxies, stars, and gas across an immense scale. For all its grandeur, this celestial titan is not an immortal entity. One day, its stars will fade, its black hole will quiet, and its surroundings will slip beyond the cosmic horizon. But for now, it remains a beacon of knowledge, a monument to the forces that have sculpted the universe. Studying this stellar leviathan continues to challenge and refine our understanding of how galaxies live, evolve, and ultimately face their cosmic fate. The environment of the celestial monarch is one of extremes. The Abell 2029 cluster, a dense conglomeration of galaxies, is suffused with hot plasma that radiates X-rays detectable by telescopes like Chandra. This cosmic furnace is fueled by gas stripped from smaller galaxies as they pass through the cluster, compressed and heated by gravitational forces. These interactions enrich the intracluster medium, creating the high-energy conditions necessary for sustained X-ray emissions. For now, this timeless sentinel stands as a reminder of cosmic grandeur, a testament to the past, a guide to the present, and a vision of the universe's inevitable fate. Despite its eventual fate, the universal titan remains a source of inspiration and discovery, challenging our understanding of the cosmos. Each new observation brings us closer to uncovering not only the nature of this galactic giant, but also the fundamental forces that shape the universe itself. The primordial Colossus, sometimes revered as the king of galactic giants, stands as a monument to the immense creative and destructive forces at play in the cosmos. Its story, spanning billions of years, is a narrative of formation, destruction, and rebirth, a microcosm of the universe's constant flux. This galactic juggernaut embodies both the beauty and the violence of large-scale cosmic evolution, offering an unparalleled laboratory for exploring the mechanics of the universe. At its heart lies a region of unfathomable energy and density, a supermassive black hole, often referred to as the engine of eternity. This gravitational leviathan does more than consume, it transforms. Gas and dust drawn into its event horizon are either devoured or ejected in powerful relativistic jets, traveling near the speed of light. These outflows heat surrounding gas, preventing new stars from forming and shaping the broader structure of the galaxy. This dark monarch at the galaxy's core is both a creator and a destroyer, continuously influencing the evolution of its host. Moving outward from this gravitational abyss, the structure of the galaxy itself stands as a testament to endurance, sometimes romantically termed the stellar palace. It houses trillions of stars, many of which have long outlived their prime. These ancient suns, dimmed and reddened by time, are relics of a distant epoch when the galaxy teemed with star-forming activity. Today, their soft radiance gives the celestial elder its characteristic golden hue, a reminder of its advanced stage of evolution. Beyond this warm glow, an even more elusive component, dark matter, the silent architect of the cosmos. This unseen force envelops the galaxy, providing the gravitational cohesion necessary to maintain its vast structure. The dark halo surrounding the stellar leviathan extends millions of light years beyond its luminous core, not only holding the galaxy together, but also influencing the entire Abell 2029 cluster. The cluster itself, sometimes described as the arena of giants, is a battlefield of cosmic interactions. Smaller galaxies, drawn toward the universal colossus, spiral into its gravitational grip, stripped of their gas and stars before being absorbed. The remnants of these encounters are scattered throughout the cluster in the form of intracluster light, faint glimmers of stars torn from their original homes. This ghostly veil of Abell 2029 tells a silent story of galactic cannibalism, marking the violent history that has fueled the growth of this enormous system. Adding another layer of intrigue to this environment is the superheated plasma that fills the cluster's vast expanse. This cosmic furnace glows brilliantly in X-rays, revealing the turbulent processes that have shaped Abell 2029 over billions of years. Galactic collisions and mergers continuously churn this high-energy medium, keeping it at extreme temperatures. Paradoxically, this plasma, while binding the cluster together, also signals the end of star formation by preventing gas from cooling enough to condense into new stars. This delicate balance of creation and destruction defines the ecosystem of the stellar sovereign. As astrophysicists continue to probe the depths of this cosmic giant, its mysteries deepen. Each layer of its structure tells a different part of the story. The gravitational heart pulsing at its core, the ancient stellar palace glowing in quiet grandeur, the vast dark halo dictating its stability, and the luminous trails of lost stars drifting in the cluster's gravitational sea. These interwoven elements remind us that even the most massive structures in the universe are shaped by an intricate dance of forces, stretching across billions of years. Ultimately, this celestial titan stands as one of the greatest testaments to the universe's power, complexity, and endless potential. While it will one day fade into the growing void of an ever-expanding cosmos, its legacy will endure in the knowledge it provides, guiding future explorations into the nature of galaxies, black holes, and the unseen forces that govern reality itself. As we peer deeper into the stellar abyss of this galactic giant, its past becomes even more compelling. How many galaxies did it consume to reach its current size? What were the dynamics of those mergers? Astronomers have detected faint tidal streams, remnants of galaxies torn apart by its immense gravitational pull, offering glimpses into its turbulent history. Each stream, Each ripple of starlight is a chapter in a saga of cosmic dominance, written over eons, beyond being a relic of the past. This silent titan also holds clues about the universe's future. As the cosmos continues to expand, massive ellipticals like this one provide a vision of what may become of galactic clusters in the distant future. Over billions of years, the Milky Way and its neighbors may merge into a single behemoth, much like this future vision of galactic evolution. This realization lends a personal dimension to the study of this distant leviathan, linking humanity's cosmic home to the broader narrative of time and transformation. Despite its grandeur, the eternal beacon is not immortal. Over unfathomable spans of time, its stars will exhaust their fuel, fading into remnants like white dwarfs and neutron stars. The black hole at its core, once a voracious consumer of matter, will eventually fall silent, emitting only the faintest traces of energy. In the final stages of the universe, this once luminous giant will dim into a cold, dark remnant. This inevitable fate, though sobering, is a poignant reminder that even the most colossal structures are transient in the grand design of the cosmos. Yet, for now, the stellar emperor shines on, a marvel of cosmic architecture and a testament to the power of gravity, dark matter, and time. It remains a focal point of human curiosity, pushing the boundaries of astrophysical research. More than just a galaxy, it is a monument to cosmic evolution, a beacon of the universe's ability to create both beauty and complexity on unimaginable scales. The eternal colossus of Abell 2029, sometimes called the silent architect of cosmic history, continues to captivate astronomers and philosophers alike. Spanning over 6 million light-years, this titan of the cosmos stands as a testament to the scale, complexity, and dynamism of the universe, an artifact of ancient mergers, relentless gravitational dominance, and the steady march of time. At its core lies one of the most enigmatic forces in existence, a supermassive black hole, often referred to as the abyssal monarch. This immense singularity wields a gravitational influence so profound that it dictates not only the fate of its host galaxy, but also the surrounding cluster. Matter spiraling into this void generates torrents of high-energy emissions, transforming the black hole into a beacon at the heart of a slowly aging structure. Yet, this dark sovereign is more than a consumer. It is a shaper of galaxies. As it devours matter, it releases immense radiation and energy, heating surrounding gas in a process known as feedback. This cosmic paradox, where a black hole both suppresses and sustains galactic growth, plays a crucial role in stabilizing the galactic sovereign, ensuring its continued reign over the Abell 2029 cluster. The stars of this timeless titan, often described as the golden relics of the cosmos, are among the oldest in the universe. Glowing in muted shades of yellow and red, they stand as remnants of a bygone era when the galaxy was young and bursting with stellar birth. Now, the stellar tapestry of this celestial leviathan is woven from aging giants, their fuel nearly spent, their once vibrant light fading into cosmic memory. The lack of cool gas and newborn stars gives the system its signature stillness, a tranquil facade concealing the violent history of its evolution. Encircling this ancient core is the cosmic shroud of intracluster light, a faint, ghostly glow from stars torn from their original galaxies during past mergers. These drifting cosmic vagabonds serve as spectral reminders of the many galactic bodies that were absorbed into the greater whole. By studying this stellar haze, astronomers can retrace the steps of its violent past, deciphering the collisions and mergers that built this celestial empire. Yet, the true scale of the celestial giant becomes evident when considering its dark matter halo, sometimes referred to as the invisible crown of Abell 2029. This vast, unseen structure extends far beyond its luminous core, providing the gravitational foundation necessary for its immense size and stability. More than just a binding force, This dark foundation dictates the motion of thousands of smaller galaxies within the cluster, shaping their interactions and long-term fates. Unraveling the mysteries of this halo is essential to understanding dark matter, one of the universe's most elusive and fundamental components. The Abell 2029 cluster, often described as the cosmic cauldron, is a theater of galactic interactions. Smaller galaxies, unable to resist the gravitational draw of the universal colossus, spiral toward it, stripped of gas and stars before being consumed. Their remnants linger as dim streams of light, forming what astronomers call the ghostly veil of Abell 2029. This diffuse glow is a silent record of galactic cannibalism, a testament to the relentless cycle of mergers that has shaped this enormous system. Adding to its enigmatic nature is the vast ocean of superheated plasma that permeates the cluster, known as the cosmic furnace. This X-ray bright medium, sustained by the turbulence of galactic collisions, serves as both the glue holding the cluster together and a barrier preventing new star formation. Its intense heat keeps interstellar gas from cooling, ensuring that stellar nurseries remain dormant. This delicate balance of creation and destruction defines the ever-changing fate of this stellar sovereign, as astrophysicists continue to probe the depths of this cosmic giant. Its mysteries deepen. Every layer of its structure, the gravitational heart, the ancient stellar palace, the cosmic shroud of lost stars, and the vast dark halo reveals a different piece of the puzzle, each one unlocking more secrets of the universe's grand design. One day, as the universe expands ever outward, this celestial titan will stand alone, a silent witness to the passage of cosmic time. Yet even in solitude, it will remain a monument to the forces that sculpt the cosmos. Its presence in the sky serves as a challenge, urging humanity to reach further, to question deeper, and to seek the hidden mechanisms of reality. For now, the stellar emperor continues its reign, offering a window into the distant past while illuminating the pathways that lead toward the future. As long as its light reaches us, it will remind us of our place in the cosmos and the endless wonders that await discovery. The universal sovereign is not merely a component of its cluster, it governs it. Its immense gravitational pull, amplified by its dark matter halo, dictates the motions of surrounding galaxies, shaping the entire Abell 2029 system. This influence extends for millions of light years, making this colossal galaxy more than just a celestial body. It is the central anchor of a vast cosmic ecosystem. The gravitational interactions it drives ensure the cluster's ongoing evolution, fueling its dynamic and ever-changing structure. Observing this stellar colossus is a study in cosmic history and future potential. Often described as a cosmic time capsule, it holds within its vast expanse a record of nearly the entire history of the universe. Every faint stream of intracluster light, every ripple of dark matter, and every ancient star is a fragment of a grand puzzle, a silent archive chronicling the transformation of the cosmos from its infancy to the present day. This eternal beacon also offers a glimpse into the distant future. As galaxies within the Abell 2029 cluster continue to merge and evolve, this leviathan will likely grow even larger, absorbing more matter and further consolidating its dominance. Over time, as the universe expands, this cosmic monarch will become isolated, trapped in an ever-growing void. Trillions of years from now, its stars will fade, leaving behind only remnants, a cold, dark relic of a universe once filled with brilliance. For now, however, this universal titan remains a masterpiece of cosmic engineering, a living testament to the forces that shape the largest structures in existence. It challenges us to think beyond the limits of human experience, to grasp the vastness of the universe and the mysteries it holds. Every new insight into this galactic colossus brings us closer to understanding the broader workings of the cosmos. This silent titan of the cosmos, sometimes referred to as the galactic monarch of eternity, looms as an enduring enigma, a celestial fortress whose grandeur surpasses even the wildest imaginations of cosmic explorers. It invites endless speculation, stirring curiosity about the secrets hidden within its colossal structure. Spanning over 6 million light-years, this stellar leviathan exists on a scale that defies conventional understanding. To grasp its enormity is to confront the unfathomable. It could engulf thousands of galaxies, the size of the Milky Way. How did this cosmic colossus attain such magnitude? Its origins are rooted in galactic collisions, mergers, and relentless cannibalism, a testament to a universe in perpetual motion, where destruction begets creation on an incomprehensible scale. At its heart, the Abyssal Emperor, a supermassive black hole of unimaginable mass, reigns over this galactic dominion, estimated at more than 40 billion times the mass of the Sun. This dark heart influences not only its host galaxy, but the entire Abell 2029 cluster. Sometimes called the cosmic maelstrom, this singularity devours matter with insatiable hunger, unleashing violent jets of energy that cut through space like cosmic spears. Yet, paradoxically, it suppresses star formation, ensuring that this ancient structure remains tranquil, undisturbed by the chaos it once fed upon. The galactic core, often described as the Golden Throne, is a dense concentration of ancient stars, their once brilliant light softened by the passage of billions of years. These stellar relics, clustered tightly in the central regions, form a radiant hub of golden hues. The absence of young, blue stars in this stellar mausoleum signals the long-dormant era of star formation. Yet, though this galaxy has aged, its influence endures, a silent architect in the grand theater of galactic evolution. Encircling the stellar monarch is its ethereal halo, a region known as the Veil of Lost Galaxies. This vast expanse of faintly glowing light consists of intracluster stars, cosmic orphans stripped from their homes during past mergers, drifting aimlessly through the void. These unbound stars remain within the gravitational grasp of the cluster, their ghostly luminescence, detectable only with the most sensitive instruments, serves as a haunting reminder of the violent history that sculpted this great cosmic entity over billions of years. Yet, the visible components of this galaxy, as immense as they are, tell only part of the story. Encasing the timeless sovereign is a dark matter halo, an unseen force that provides the structural foundation for its staggering size. This shadow crown extends far beyond its luminous boundaries, shaping not just its own fate, but that of the entire Abell 2029 cluster. Without this hidden framework, the gravity needed to bind such an immense structure together would not exist. Understanding this dark halo is key to unlocking the deeper mechanics governing the universe. The environment surrounding this eternal colossus is as fascinating as the galaxy itself. The Abell 2029 cluster, sometimes described as the cosmic battleground, is a dense region of space teeming with smaller galaxies, each navigating the gravitational currents of the colossal system. Over billions of years, these galaxies have been drawn toward the cluster's center, stripped of their gas and stars before becoming part of the expanding mass of the dominant galaxy. This cosmic furnace glows in X-rays, illuminating the ongoing high-energy processes that shape the cluster's structure. The interplay between this stellar overlord and its environment is an active and evolving process. As it continues its reign, smaller galaxies succumb to its gravitational pull, their material merging with the expanding mass of the colossus. This relentless cycle ensures that the galaxy will only grow larger, solidifying its status as the ultimate galactic predator. Yet, paradoxically, even as it consumes, it stabilizes, anchoring the cluster and preventing its galaxies from drifting into the cosmic abyss. Studying this universal titan is a lesson in cosmic fragility. The light we observe from this galaxy today is a message from hundreds of millions of years ago, a window into a past, both distant and inspiring. This celestial monument bridges time and space, connecting the present to the earliest epochs of the universe and offering a glimpse into its eventual fate. The story of this galactic sovereign is ultimately the story of the universe itself, a saga of relentless expansion, transformation, and survival. It stands as a reminder of the infinite possibilities that lie within the cosmos, urging us to explore, to question, and to marvel at the mysteries hidden in the depths of space. The cosmic monarch of eternity, often regarded as the eternal ruler of galactic evolution, remains both a scientific enigma and a philosophical wonder. More than just an object of study, this stellar juggernaut of Virgo continues to intrigue those who seek answers about existence, time, and the ultimate fate of the universe. This celestial leviathan is not merely a relic of the past, it is a silent storyteller, a relic of creation whispering tales from the dawn of time. The gravitational sovereign at the heart of this immense galaxy is a force beyond human comprehension, one of the largest supermassive black holes ever detected. It serves as the galaxy's central engine, consuming matter that ventures too close while unleashing immense energy. The X-ray emissions from its accretion disk reveal the staggering temperatures and chaotic forces at play within this cosmic abyss. These emissions are not merely echoes of destruction, they are windows into the deepest laws of the universe, offering astronomers invaluable insights into the nature of spacetime, gravity, and energy. Yet, the influence of this dark core extends far beyond its immediate vicinity. The energy released from the black hole radiates outward, heating gas within both the galaxy and the surrounding Abell 2029 cluster. This process, known as active galactic nucleus feedback, prevents the cooling of gas that would otherwise fuel new star formation. In this way, the cosmic maelstrom shapes the galaxy's future, halting stellar birth while ensuring its continued existence as an ancient, colossal structure. This paradox where destruction sustains longevity lies at the heart of the galaxy's evolution. As the universe expands, galaxies like this one will drift into isolation, their once thriving clusters stretching into the cosmic abyss. Trillions of years from now, the stars within this behemoth will fade, leaving behind only remnants: white dwarfs, neutron stars, and black holes. The supermassive black hole at its core, once a voracious consumer, will eventually fall silent, emitting only faint whispers of radiation as it slowly evaporates over eons. Yet, for now, this universal titan shines on, its light traversing the vast cosmic expanse, a testament to the forces that shape the grandest structures in existence. It is a monument to cosmic evolution, a beacon of the universe's ability to craft beauty and complexity on unimaginable scales. The stellar cathedral of this galactic colossus is a testament to the vast forces that have shaped it over billions of years. Within its core, some of the oldest stars in existence remain as relics of a time when this galaxy was young, filled with the raw material of creation. Now, these ancient suns cluster together in a dense, golden-hued mass, their light softened by eons of cosmic evolution. Subtle fluctuations in their brightness and motion reveal traces of past mergers, the gravitational echoes of long-lost galaxies now absorbed into this immense structure. Beyond its visible expanse, a ghostly veil stretches into the darkness, a shroud of lost galaxies, composed of stars that were stripped from their original homes during past encounters. No longer tethered to any single system, these celestial wanderers drift through the vastness of the cluster, forming what astronomers call intracluster light. This faint, ethereal glow is more than just a remnant of destruction. It is a silent archive of the violent interactions that have defined this galaxy's relentless expansion. Encasing this behemoth is a dark matter halo, an unseen but all-encompassing scaffold of gravity that extends well beyond its luminous boundaries. Without this invisible framework, the galaxy's immense size and structure would be impossible. Its stars and gas would simply drift apart into the void. This dark foundation not only anchors the galaxy, but also shapes the motion of thousands of smaller galaxies within its cluster. Understanding this vast, hidden component remains one of the greatest challenges in modern astrophysics. as it may hold the key to unraveling the true nature of the cosmos itself. The surrounding cluster is a dynamic battlefield, where galaxies are drawn toward the gravitational might of this cosmic predator, stripped of their material, and ultimately consumed. These encounters fuel a superheated sea of plasma, a reservoir of X-ray emitting energy that illuminates the structure of the cluster. This fiery medium, sustained by eons of galactic collisions and black hole activity, reveals the turbulent processes that govern the long-term evolution of this region. Yet, despite its apparent stability, this galaxy is not immutable. Every faint stream of light, every displaced star, every trail of cosmic debris whispers of past destruction of smaller galaxies torn apart, their material absorbed, their identities lost within the ever-growing expanse of this celestial leviathan. It is both a relic of the past and a force that continues to shape the fabric of the cosmos itself. As the universe expands, this galactic titan will eventually become an isolated island of light, drifting alone in an increasingly dark and empty void. Over trillions of years, the last of its stars will fade, leaving behind only remnants: white dwarfs, neutron stars, and black holes. Its supermassive black hole, once a ravenous force of gravity, will grow silent, emitting only faint whispers of energy as it slowly decays. For now, though, this celestial monarch endures, its light reaching us across hundreds of millions of light-years, a beacon illuminating the depths of time and space. It stands as a monument to the invisible forces that shape the universe, reminder of the boundless creativity of the cosmos, and a challenge to our understanding of galactic evolution. This timeless titan inspires profound questions. How did the universe come to be? What forces dictate its fate? What role do galaxies like this play in the grander scheme of cosmic history? Every photon of light that reaches us from this immense structure carries the echoes of an ancient past, urging us to look beyond the limits of human understanding, more than just a galaxy. This stellar colossus is a symbol of cosmic entrance, testament to the grand scale of time, space, and gravitational power. It is not merely an object of study, but a celestial storyteller, whispering tales of creation, destruction, and the relentless march of time. Beyond its visible structure lies a ghostly veil of intracluster light, a diffuse, ethereal glow from countless stars that were stripped from their parent galaxies and set adrift within the Abell 2029 cluster. These orphan stars, no longer bound to any singular home, drift in the vast sea of gravitational currents, silent witnesses to the cosmic battles of creation and destruction. Their faint light is a whisper of past turmoil, a quiet testament to the violent history of mergers and interactions that sculpted this stellar colossus into the behemoth it is today. Enclosing this empire of stars is its invisible throne, a dark matter halo that defines its true scale and gravitational might. This unseen framework, composed of enigmatic particles yet to be fully understood, is the hidden foundation upon which this galaxy's dominance rests. Extending well beyond its luminous core, this massive halo anchors the entire Abell 2029 cluster, influencing the orbits of thousands of smaller galaxies and maintaining the delicate equilibrium of this vast cosmic system. The surrounding cluster, often referred to as a cosmic furnace, is a realm of high-energy interactions where galaxies collide, evolve, and ultimately succumb to the relentless pull of gravitational forces. At its core, a vast reservoir of superheated plasma glows in X-ray wavelengths, a fiery consequence of the gas stripped from infalling galaxies. This cosmic fire, fueled by the remnants of stellar explosions and galactic collisions, enriches the intracluster medium, forging new elements and reshaping the environment in a never-ending cycle of transformation. Yet, even as it reigns over the cluster, this celestial monarch is not immune to the relentless expansion of the universe. As dark energy accelerates the stretching of spacetime, galaxy clusters will drift ever further apart, their ancient light fading into the abyss. In the distant future, IC 1101 will become an isolated beacon in an empty universe, disconnected from all but the stars trapped within its gravitational embrace. Over trillions of years, its brilliance will wane. Its stars will wither into white dwarfs, neutron stars, and black holes, and its once mighty core will grow silent. Even its dark sovereign, the supermassive black hole that once shaped its destiny, will not last forever. Over unimaginable eons, it will slowly evaporate through the quiet process of Hawking radiation, disappearing into the void. The immortal sentinel, once the heart of an empire spanning millions of light years, will fade into a shadow of its former self, a cold, dark monument to an era long past. Yet, the story of this cosmic titan is not one of mere decline, but of entrance and transformation. Every collision, every merger, every upheaval that led to its formation is etched into the larger history of the universe itself. The galaxies it consumed, the elements it spread, the stars it nurtured all have played a role in shaping the cosmos. For humanity, IC 1101 is more than an astronomical curiosity. It is a mirror to our own existence. It humbles us, reminding us that our time in the cosmos is but a fleeting moment against the backdrop of eternity. Yet, it also inspires us, driving us to seek, to wonder, to push the limits of our understanding. Its golden glow carries whispers from the past, its massive halo binds together an entire cluster, and its central abyss hints at the deepest mysteries of space-time itself. As scientists peer ever deeper into its ancient light, they uncover not just the story of a galaxy, but the story of the universe itself. IC 1101, the timeless sovereign of the stars, is more than just a remnant of the past. It is a beacon guiding us toward the future, illuminating the cosmic pathways we have yet to explore. Even as its final fate is sealed, this eternal Galaxies leaves behind a legacy written in the very fabric of space and time. It reminds us that even the grandest structures are impermanent, that the universe is in a constant state of flux, and that within that impermanence lies an unparalleled beauty, a beauty that compels us to explore, to question, and to embrace the infinite possibilities of the cosmos. The story of this cosmic titan is not just the story of a galaxy, it is our story as well. In its unfathomable scale and incomprehensible history, we find both awe and belonging. It stands as a testament to the forces that shape existence, to the relentless march of time, and to the delicate balance between creation and destruction, entrance and transformation. And in that realization, we glimpse a fundamental truth. In the vast expanse of space and time, we are all part of something far greater than ourselves.
A supernova is one of the most powerful and awe-inspiring events in the universe, marking the explosive death of a massive star. These cataclysmic outbursts release more energy in a few seconds than our sun will emit in its entire lifetime, briefly outshining entire galaxies. Supernovae play a crucial role in cosmic evolution, dispersing heavy elements into space and seeding the next generation of stars and planets. There are two main types of supernovae, core-collapse and thermonuclear. Core-collapse supernovae occur when a massive star, at least 8 times the mass of the Sun, exhausts its nuclear fuel. Without the outward pressure of fusion, gravity causes the core to collapse, triggering a violent explosion. The remnant may form a neutron star or, if the core is massive enough, a black hole. Thermonuclear supernovae, on the other hand, happen when a white dwarf in a binary system accumulates too much mass from a companion star. This excess material triggers a runaway nuclear reaction, obliterating the white dwarf in a brilliant flash. Supernovae serve as cosmic factories for elements like iron, nickel, and gold. In fact, the calcium in our bones and the iron in our blood were forged in these stellar explosions billions of years ago. Without supernovae, the universe would lack many of the elements essential for life. Beyond their role in chemical enrichment, supernovae influence galactic dynamics. Their shock waves trigger the formation of new stars by compressing interstellar gas clouds. Some supernovae leave behind remnants like the Crab Nebula, which continues to expand centuries after the initial explosion, providing astronomers with valuable insights into stellar death and rebirth. These stellar explosions are also crucial cosmic beacons. Type Ia supernovae, for example, have a consistent peak luminosity, making them essential for measuring vast cosmic distances. By studying these standard candles, astronomers have determined that the universe is expanding at an accelerating rate, leading to the discovery of dark energy, a mysterious force driving cosmic expansion. The study of supernovae is not just a matter of astronomical curiosity, it has practical implications for Earth. A supernova occurring within 50 light-years could pose a significant threat to our planet, stripping away the ozone layer and exposing life to lethal radiation. Fortunately, no nearby stars are currently on the verge of such an explosion. Supernovae also produce some of the most exotic objects in the cosmos. A core collapse event can result in the formation of a neutron star, an ultra-dense remnant where a sugar cube-sized piece of material would weigh as much as Mount Everest. Some neutron stars become pulsars, spinning rapidly and emitting beams of electromagnetic radiation. If the collapsing core is massive enough, it forms a black hole, an object with gravity so intense that not even light can escape. The first recorded supernova visible to the naked eye was observed by Chinese astronomers in 185 CE. Since then, historical records have documented several spectacular events, including the famous SN 1054, which created the Crab Nebula, and Kepler's supernova of 1604, which shone brightly for weeks. Today, astronomers use powerful telescopes like Hubble and the Vera C. Rubin Observatory to detect and study these cosmic detonations. Supernovae also generate powerful neutrino bursts, subatomic particles that barely interact with matter. The detection of neutrinos from SN 1987A in the Large Magellanic Cloud confirmed key theories about stellar collapse and provided rare direct observational data on the inner workings of a dying star. Some supernovae challenge our understanding of stellar physics. Hypernovae, for instance, are even more energetic than regular supernovae and may be linked to long-duration gamma-ray bursts, the most intense explosions in the universe. The nature of so-called superluminous supernovae, which shine 10 times brighter than ordinary supernovae, remains an active area of research. Another mystery is the fate of Betelgeuse, a red supergiant in the Orion constellation. This massive star is nearing the end of its life and could explode in the next few thousand years, or even tomorrow. If it does, it will be visible in broad daylight from Earth, offering humanity a front-row seat to one of the most extraordinary cosmic events. Supernovae not only illuminate the past but also shape the future of astrophysics. Scientists are using advanced simulations, high-energy observatories, and gravitational wave detectors to probe the secrets of these stellar cataclysms. Understanding supernovae could help answer fundamental questions about the nature of matter, the origins of elements, and the ultimate fate of the universe. The next nearby supernova could revolutionize our understanding of the cosmos. Telescopes worldwide are constantly scanning the sky, hoping to catch the next great stellar explosion in real time. When it happens, astronomers will be ready. Supernovae are also responsible for some of the most extreme and mysterious phenomena in the universe, including magnetars. Magnetars are highly magnetized neutron stars, with magnetic fields trillions of times stronger than Earth's. These bizarre remnants occasionally release powerful bursts of X-rays and gamma rays, capable of affecting our planet's upper atmosphere even from thousands of light-years away. The origin of magnetars is still debated, but many scientists believe they are born from the most energetic core-collapse supernovae. Another intriguing class of stellar explosions is the so-called failed supernova. In these rare cases, a massive star collapses directly into a black hole without producing a visible explosion. Some astronomers have observed stars that seem to vanish without a trace, hinting that direct collapse black hole formation might be more common than previously thought. If confirmed, this could reshape our understanding of how black holes form and evolve. Supernovae are not only natural laboratories for studying high-energy physics, but they also play a role in shaping entire galaxies. When a supernova explodes, it injects vast amounts of energy into the surrounding interstellar medium. This feedback process can regulate star formation by either compressing gas clouds to trigger new star birth or dispersing gas and preventing further star formation. In extreme cases, multiple supernovae can create superbubbles, vast cavities in galaxies filled with hot, ionized gas. The Milky Way itself has been shaped by countless supernovae over billions of years. Some astronomers suspect that past supernova explosions may have influenced the evolution of life on Earth. The hypothesis of a supernova-induced mass extinction suggests that cosmic rays from a nearby explosion could have altered Earth's atmosphere, leading to climate change or increased mutation rates. While no definitive evidence links a supernova to past extinctions, isotopic traces of iron-60 found in deep-sea sediments suggest that at least one supernova occurred relatively close to Earth within the last few million years. The search for supernovae extends beyond our own galaxy. Astronomers regularly discover and analyze supernovae in distant galaxies, using powerful telescopes like the James Webb Space Telescope. These extragalactic supernovae provide crucial data for understanding the early universe, as they offer glimpses into the lives and deaths of the first generations of stars. Some of the earliest supernovae may have contributed to the reionization of the universe, a period when the first stars and galaxies transformed the cosmos from a dark, neutral state into the bright, structured universe we see today. The interplay between supernovae and cosmic rays is another fascinating area of research. Supernova remnants, like the famous Tycho and Cassiopeia A remnants, are believed to be primary accelerators of cosmic rays, high-energy particles that travel near the speed of light. When these charged particles collide with the interstellar medium, they produce gamma rays, which can be detected by space telescopes. Understanding the origins of cosmic rays could shed light on some of the most energetic processes in the universe. In recent years, astronomers have begun using machine learning and artificial intelligence to detect and classify supernovae more efficiently. Automated surveys like the Zwicky Transient Facility, ZTF, and the upcoming Legacy Survey of Space and Time, LSST, are expected to discover thousands of new supernovae every year. These vast datasets will help refine theoretical models and potentially uncover new, exotic types of stellar explosions that defy current classification. Another breakthrough in supernova studies came with the advent of gravitational wave astronomy. When two neutron stars collide, a process often initiated by a supernova, they produce both a visible explosion, called a kilonova, and gravitational waves, ripples in spacetime first predicted by Einstein. The detection of gravitational waves from the neutron-star merger GW170817 confirmed that kilonovae are responsible for creating heavy elements like gold and platinum, solving a long-standing astrophysical mystery. As technology advances, astronomers hope to capture a supernova in the earliest stages of its explosion, something that has rarely been observed in real time. Supernova early warning systems, which monitor nearby stars for pre-explosion activity, may soon allow scientists to predict and study these stellar deaths as they unfold. If successful, such efforts could provide unprecedented insights into the final moments of massive stars. Even in death, supernovae continue to shape the universe in ways we are only beginning to understand. Their explosive legacies live on in the stars that form from their remnants, in the elements that compose planets and life itself, and in the mysteries they leave for future generations to explore. Supernovae are not just violent endings, they are also cosmic rebirths, setting the stage for the next generation of stars, planets, and even life. The elements forged in these titanic explosions, carbon, oxygen, silicon, iron, and countless others, become the building blocks of everything we see around us. Every atom in our bodies heavier than hydrogen and helium was, at some point, created in the heart of a massive star and released into space by a supernova. In this sense, we are all made of stardust. One of the most enigmatic consequences of supernovae is the creation of exotic objects like quark stars, a hypothetical state of matter even denser than neutron stars. Some physicists speculate that under extreme pressure, neutrons in a collapsed star could break down into their constituent quarks, forming an incredibly compact remnant. While no confirmed quark stars have been observed, ongoing studies of unusually massive neutron stars suggest that these strange objects might exist. Supernovae are also responsible for some of the most luminous transient events in the cosmos. One such phenomenon is the parainstability supernova, a rare explosion that occurs in extremely massive stars, at least 150 times the mass of the Sun. Unlike typical core-collapse supernovae, which leave behind a remnant, parainstability supernovae completely annihilate the star, leaving no black hole or neutron star behind. These colossal explosions were likely more common in the early universe when massive first-generation stars dominated. Another fascinating class of explosions is the so-called zombie or repeating supernova. Some supernovae, like the peculiar IPTF-14HLS, have defied expectations by exploding multiple times over several years instead of fading away. This challenges existing models of stellar death and suggests that some massive stars may undergo prolonged, episodic eruptions before finally collapsing for good. Supernova remnants, though often associated with destruction, can also be sites of intense astrophysical activity. Pulsar wind nebulae, for instance, form when a rapidly spinning neutron star, or pulsar, injects high-energy particles into its surrounding environment. One of the most famous examples is the Crab Nebula, which houses a central pulsar that rotates 30 times per second, emitting beams of radiation that sweep across space like a cosmic lighthouse. The effects of supernovae extend far beyond their immediate surroundings. Some researchers believe that the cosmic rays generated by supernovae may have influenced Earth's climate over geological timescales. The hypothesis, known as the cosmic ray climate connection, suggests that variations in supernova activity in our galactic neighborhood could affect cloud formation and, consequently, global temperatures. If true, this would mean that the history of life on Earth has been subtly shaped by distant stellar explosions. From a technological standpoint, the study of supernovae has led to innovations that extend beyond astrophysics. The techniques developed to detect and analyze supernovae, such as advanced image processing, machine learning, and high-energy particle detection, have applications in medical imaging, nuclear physics, and even materials science. The hunt for neutrinos from supernovae has also inspired the construction of massive underground detectors, which are now used for monitoring nuclear activity and searching for rare particle interactions. Looking forward, astronomers are eagerly anticipating the next nearby supernova, as it would provide an unprecedented opportunity to study these cosmic explosions up close. Some candidates, like Betelgeuse and Eta Carinae, are closely monitored for signs of impending collapse. When the next supernova occurs in the Milky Way, it will not only be a spectacular sight but also a moment of scientific discovery, potentially answering long-standing questions about stellar evolution, nucleosynthesis, and the nature of extreme matter. As we peer deeper into the universe with increasingly sophisticated telescopes, we continue to uncover new mysteries about these celestial explosions. Each supernova, whether a fiery death or a rebirth of cosmic matter, tells a story of transformation, destruction, and creation, a cycle that has shaped the universe for billions of years and will continue to do so for eons to come. Supernovae are also key players in the cosmic web, the vast structure of galaxies, filaments, and voids that define the large-scale architecture of the universe. When a supernova explodes, it not only enriches its host galaxy with heavy elements but also injects immense kinetic energy into the interstellar medium. This energy influences star formation rates and can even drive galactic winds, powerful outflows of gas that regulate a galaxy's growth and evolution. In extreme cases, these winds may strip galaxies of their star-forming material entirely, leading to the eventual death of a galaxy. Some of the most puzzling supernovae are those associated with gamma-ray bursts, GRBs, the most energetic explosions known. Long-duration GRBs are thought to arise from the deaths of particularly massive stars, where the collapsing core forms a rapidly spinning black hole. This process generates twin jets of relativistic plasma that pierce through the dying star, releasing an immense burst of gamma rays detectable across billions of light-years. GRBs are so powerful that a single event can briefly outshine all the stars in its host galaxy combined. Scientists are still unraveling the precise mechanisms behind these extreme events and their role in shaping the universe. Another fascinating phenomenon linked to supernovae is the presence of runaway stars. These are high-velocity stars that have been ejected from their home systems due to a supernova explosion. When a massive star in a binary system explodes, the sudden loss of mass can send its surviving companion hurtling through space at incredible speeds. Some runaway stars are traveling so fast that they may eventually escape the Milky Way entirely, becoming intergalactic wanderers. Supernovae also play a crucial role in one of the biggest mysteries in cosmology, dark energy. Observations of Type Ia supernovae in distant galaxies revealed that the universe's expansion is not slowing down due to gravity but is instead accelerating. This groundbreaking discovery, which earned the 2011 Nobel Prize in Physics, suggested the existence of dark energy, an unknown force that makes up roughly 70% of the universe. Without supernovae acting as cosmic mileposts, this revelation about the fundamental nature of the cosmos might never have been made. Even within our own solar system, evidence of past supernovae can be found. Scientists have discovered traces of iron-60, an isotope produced in supernovae, embedded in Earth's deep-sea sediments, on the Moon, and even in Antarctic ice. These findings suggest that one or more nearby supernovae may have occurred within the last few million years, possibly influencing Earth's environment in subtle ways. Some researchers speculate that these explosions may have contributed to evolutionary changes by increasing mutation rates or altering atmospheric chemistry. The future of supernova research is brighter than ever. Upcoming space missions, such as the Nancy Grace Roman Space Telescope, will survey the sky for new supernovae, helping refine our understanding of dark energy and the expansion of the universe. Meanwhile, ground-based observatories like the Extremely Large Telescope, ELT, will allow astronomers to study supernova progenitors in unprecedented detail, potentially identifying stars on the brink of explosion before they go supernova. One of the most ambitious projects in astrophysics today is the effort to detect a supernova in real time from its earliest moments. By monitoring massive stars with space-based observatories and neutrino detectors, scientists hope to catch the very first signals of a supernova, before the explosion even becomes visible. This would allow for an unparalleled observational campaign, capturing every stage of the event as it unfolds. Supernovae are reminders that the universe is dynamic, ever-changing, and interconnected in ways we are only beginning to grasp. From their role in forging the elements that make up planets and life to their influence on the evolution of galaxies and the expansion of the cosmos, these stellar explosions are among the most important and awe-inspiring phenomena in nature. The next supernova could be discovered at any moment, and when it does, it will undoubtedly bring new insights into the workings of the universe. Supernovae are also linked to some of the most extreme astrophysical environments in the universe, including accretion disks around black holes and the violent interactions within dense star clusters. When a supernova occurs in a crowded stellar environment, such as a globular cluster or the core of a galaxy, the energy released can disrupt surrounding stars, trigger new waves of star formation, or even influence the motion of nearby black holes. Some astronomers believe that repeated supernova explosions in the centers of galaxies may play a role in feeding the supermassive black holes that reside there, providing them with the matter needed to grow. Another intriguing connection between supernovae and black holes comes from the study of so-called fallback supernovae. In these cases, the initial explosion is not strong enough to fully eject the star's outer layers, causing some of the material to fall back onto the collapsed core. This process can lead to the formation of a black hole rather than a neutron star and may explain why some black holes appear to be born with unexpectedly high masses. The study of fallback accretion is helping astrophysicists understand the distribution of black hole masses and the conditions under which they form. Beyond individual stars and galaxies, supernovae may also have had profound effects on the early universe itself. During the first few 100 million years after the Big Bang, the universe was filled with primordial hydrogen and helium, with little to no heavier elements. The first generations of supernovae, originating from massive population 3 stars, were responsible for producing the first heavy elements, fundamentally altering the composition of the cosmos. Without these early supernovae, later generations of stars, capable of forming planetary systems and eventually life, would never have been possible. Interestingly, supernovae may also act as natural laboratories for testing the fundamental laws of physics. The extreme conditions inside an exploding star push the boundaries of our understanding of nuclear physics, particle interactions, and even the behavior of gravity under extreme densities. For example, the study of neutrinos from supernovae provides insights into weak nuclear interactions, while observations of supernova remnants offer constraints on alternative theories of gravity that go beyond Einstein's general relativity. One of the most exciting developments in modern astrophysics is the growing capability to study supernovae across multiple wavelengths and messengers. Traditionally, supernovae were studied using visible light, but today, astronomers also observe them in X-rays, gamma rays, radio waves, and even through gravitational waves and neutrinos. This multi-messenger approach allows for a more complete picture of the explosion, revealing details about the supernova structure, the nature of its progenitor star, and the dynamics of the surrounding environment. For example, some supernovae produce powerful radio emissions long after the explosion has faded from visible light. These radio signals provide clues about the interaction between the supernova ejecta and the surrounding interstellar medium. In some cases, they reveal the presence of dense, previously undetected stellar winds or companion stars that shaped the explosion. Similarly, infrared observations are crucial for studying supernovae hidden behind thick clouds of dust, which would otherwise remain invisible to optical telescopes. The role of supernovae in planetary system formation is another area of active research. Some scientists believe that shockwaves from nearby supernovae may have triggered the collapse of the molecular cloud that eventually formed our solar system. Isotopic anomalies in meteorites, particularly the presence of short-lived radioactive isotopes like aluminum-26, suggest that a supernova explosion may have enriched the early solar nebula, influencing the chemical composition of the planets and potentially even playing a role in the conditions that led to life on Earth. Looking even further into the future, some researchers speculate about the eventual fate of supernovae in an aging universe. As star formation slows down over cosmic timescales, the rate of supernovae will decline as well. However, even in a far future universe dominated by long-lived, low-mass stars, some forms of stellar explosions may still occur. White dwarf mergers, for instance, could continue producing Type Ia supernovae for trillions of years, providing one of the last sources of energy and illumination in an increasingly dark and quiet cosmos. Despite all that we have learned, supernovae continue to surprise astronomers with unexpected behaviors and exotic variations. Some stars defy predictions by exploding at lower or higher masses than expected, while others produce unusual light curves that challenge existing models. The discovery of new classes of supernova-like explosions, such as fast blue optical transients, FBOTs, and calcium-rich transients, suggests that our understanding of stellar deaths is still incomplete. Each new supernova observed adds another piece to the puzzle, helping refine our knowledge of how stars live and die. The study of supernovae is not merely an academic pursuit, it has profound implications for our understanding of the universe and our place within it. From the origins of elements to the fate of galaxies, from the mysteries of dark energy to the physics of extreme matter, these stellar explosions hold the keys to some of the biggest questions in science. As new telescopes, detectors, and technologies come online, the next generation of astronomers will continue uncovering the secrets hidden within these cosmic firestorms, ensuring that the story of supernovae is far from over. Supernovae also serve as cosmic time capsules, preserving information about the physical conditions of the universe at different epochs. By studying the remnants of past explosions, astronomers can reconstruct details about the environment in which these stars lived and died. In some cases, supernova remnants contain traces of interactions with dark matter, offering a potential observational window into one of the greatest mysteries in modern physics. One of the most fascinating and poorly understood aspects of supernovae is their potential connection to fast radio bursts, FRBs. These mysterious millisecond-long bursts of radio waves originate from distant galaxies and often appear to be linked to magnetars, which are themselves the remnants of core-collapse supernovae. Some scientists proposed that certain FRBs may be caused by highly energetic processes occurring in young, highly magnetized neutron stars. If this connection is confirmed, it would provide another compelling example of how supernovae continue to shape the universe long after their initial explosion. Beyond their immediate astrophysical impact, supernovae have left a lasting imprint on human culture and history. The observation of bright supernovae in the night sky has been recorded in ancient Chinese, Japanese, and Middle Eastern texts. The most famous example is SN 1054, which created the Crab Nebula and was documented by astronomers across multiple civilizations. More recently, the supernova of 1572, observed by Tycho Brahe, helped challenge the prevailing Aristotelian view that the heavens were unchanging, contributing to the scientific revolution. Modern supernova discoveries continue to captivate both scientists and the general public. The advent of citizen science projects, such as the Supernova Hunters Initiative, allows amateur astronomers to participate in the discovery and classification of supernovae. With automated surveys scanning the sky every night, it is now possible for non-professionals to play a role in identifying these cosmic explosions in near real time. The growing importance of artificial intelligence, AI, in supernova research cannot be overstated. Machine learning algorithms are now used to sift through massive amounts of astronomical data, identifying supernova candidates far faster than human observers. These AI-driven techniques allow researchers to detect rare and unusual supernovae that might otherwise be overlooked. In the coming years, AI-powered sky surveys, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, are expected to catalog millions of supernovae, providing an unprecedented statistical view of stellar explosions across cosmic history. One of the most pressing open questions in astrophysics is how supernovae influence galactic habitability. While supernovae enrich the cosmos with life-essential elements, they can also pose existential threats to life on planets. If a supernova occurs too close to a planetary system, the resulting radiation and cosmic rays can strip away planetary atmospheres, disrupt biological processes, and potentially lead to mass extinctions. Understanding the frequency and distribution of supernovae helps scientists assess the long-term viability of habitable worlds in the Milky Way and beyond. Despite their destructive potential, supernovae may have also played a role in catalyzing life. Some hypotheses suggest that cosmic rays from supernovae could have influenced the chemistry of early Earth's atmosphere, helping to generate the building blocks of life. Other theories propose that the radiation from a nearby supernova could have driven evolutionary changes by increasing mutation rates, potentially accelerating the development of complex organisms. Looking ahead, future supernova research will likely focus on identifying progenitor stars before they explode. Recent observations suggest that some red supergiants undergo dramatic changes in their final years, such as shedding large amounts of mass or experiencing brief bursts of increased brightness. If astronomers can identify a star on the verge of going supernova, it would allow them to observe the explosion in unprecedented detail, potentially solving lingering questions about the exact mechanisms that trigger stellar collapse. The first-ever detection of a supernova in real time from its pre-explosion phase would mark a groundbreaking achievement in astronomy. Such an event would allow scientists to test predictive models, refine early warning systems, and possibly even observe new, unexpected physics. The combination of high-resolution telescopes, gravitational wave observatories, and deep space neutrino detectors is bringing us closer than ever to achieving this goal. Supernovae are more than just spectacular explosions, they are engines of cosmic transformation. Their impact spans the smallest subatomic interactions to the largest structures in the universe. Each new discovery brings us closer to answering fundamental questions about the origin of elements, the behavior of matter under extreme conditions, and the ultimate fate of the cosmos. The next supernova, whether in our galaxy or a distant one, will add another chapter to this ongoing story, revealing new insights into the life cycle of stars and the ever-evolving tapestry of the universe. Supernovae are not just isolated cosmic events, they are deeply interconnected with the formation and evolution of galaxies on grand scales. The sheer energy released by these stellar explosions can shape the interstellar medium, drive powerful shock waves, and regulate star formation over billions of years. Some of the most dramatic examples of this influence can be seen in starburst galaxies, where an exceptionally high rate of star formation leads to frequent supernovae that, in turn, generate massive outflows of gas and cosmic rays. In some cases, the cumulative effect of many supernovae can lead to the creation of large-scale galactic structures known as superbubbles. These are enormous cavities in the interstellar medium, often spanning hundreds of light-years, where the combined explosions of multiple supernovae have pushed away surrounding gas. Some of these superbubbles act as hotbeds for new star formation, while others may deplete a galaxy of its gas, effectively shutting down future stellar birth. Supernova-driven winds may also play a crucial role in determining whether a galaxy can sustain life-bearing planetary systems. If a galaxy experiences too many supernovae in rapid succession, the intense radiation and cosmic rays could make it difficult for planets to maintain stable atmospheres. On the other hand, too few supernovae would result in a lack of heavy elements necessary for planet formation. Understanding this balance is essential for estimating the number of potentially habitable worlds in the universe. One of the most intriguing ideas emerging from supernova research is the concept of galactic habitable zones. Just as the habitable zone around a star determines where planets can sustain liquid water, the habitable zone within a galaxy is thought to define regions where planetary systems have the best chance of developing life without being sterilized by supernovae. In the Milky Way, our solar system lies in a relatively stable region, safely distant from the galactic center, where frequent supernovae and other high-energy events might be hazardous to life. At a more fundamental level, supernovae continue to challenge our understanding of physics itself. Recent studies suggest that some supernovae may produce exotic particles beyond the standard model, such as axions or sterile neutrinos, which are hypothesized candidates for dark matter. If these particles are ever detected in the remnants of supernovae, it could revolutionize our understanding of the fundamental forces that govern the universe. Another open question in astrophysics is how certain supernovae give rise to kilonovae, explosions that occur when neutron stars merge. These events, first confirmed through the detection of both gravitational waves and electromagnetic radiation from the neutron star merger GW170817, provide strong evidence that neutron star collisions are responsible for producing many of the universe's heaviest elements, including gold, platinum, and uranium. The connection between supernovae, neutron stars, and kilonovae remains an active area of research, with each discovery shedding light on the complex life cycles of stars. The increasing precision of gravitational wave observatories, such as LIGO, Virgo, and CAGRA, is allowing astronomers to probe deeper into the physics of stellar explosions. If a supernova were to occur in the Milky Way today, gravitational wave detectors might be able to pick up signals from the violent core collapse itself, providing an entirely new way to study these cosmic events. This would be a groundbreaking achievement, as it would allow scientists to directly observe how matter behaves under the extreme conditions present during a supernova. Another exciting frontier in supernova research is the study of their role in the cosmic matter cycle. When a star explodes, it sends vast amounts of gas, dust, and metals back into space, where they eventually mix with interstellar clouds. This process enriches future generations of stars and planetary systems with the materials needed for life. Some of the elements ejected by supernovae eventually form new planets, while others drift through the cosmos for billions of years, becoming part of future nebulae, stars, or even intergalactic space. Looking toward the future, upcoming telescopes such as the Extremely Large Telescope (ELT) and the Square Kilometre Array (SKA) will revolutionize our ability to study supernovae in unprecedented detail. These next-generation observatories will allow astronomers to probe the earliest supernovae in the universe, revealing insights into how the first galaxies evolved. They will also help identify the most distant and energetic explosions, potentially uncovering new classes of supernovae that challenge existing theoretical models. Despite centuries of study, supernovae remain one of the most dynamic and enigmatic phenomena in astrophysics. Each new discovery adds to our understanding of the cosmos, revealing the intricate connections between stellar evolution, galaxy formation, and the very fabric of space and time. The next great breakthrough in supernova research could arrive at any moment, perhaps from a nearby explosion that lights up the night sky, or from a faint signal buried deep in astronomical data, waiting to be uncovered. Whatever the future holds, one thing is certain: supernovae will continue to illuminate the universe, both literally and figuratively, for generations to come. Supernovae are also crucial in the study of intergalactic enrichment, the process by which heavy elements produced in stellar explosions escape galaxies and spread into the vast cosmic voids between them. Observations of distant gas clouds have revealed traces of elements like oxygen, carbon, and iron, clear evidence that material ejected by supernovae has traveled far beyond its original galactic home. This process of enrichment influences the chemistry of future galaxies and helps shape the large-scale evolution of the universe. One of the most profound ways in which supernovae influence the cosmos is through their role in regulating the formation of stars. In dense molecular clouds, supernova shock waves can compress gas, triggering gravitational collapse and leading to the birth of new stars. This phenomenon is often observed in star-forming regions such as the Orion Nebula, where shock fronts from past supernovae have left behind intricate patterns of glowing gas and newly formed stellar clusters. In contrast, in some cases, particularly violent supernova-driven winds can sweep away gas from a galaxy entirely, suppressing star formation for millions of years. In dwarf galaxies, which have weaker gravitational holds, supernovae can play an even more dramatic role. A single powerful supernova or a series of explosions in rapid succession can eject a significant fraction of a small galaxy's gas, starving it of the raw material needed to produce new stars. Some scientists suggest that such supernova-driven outflows may explain why many dwarf galaxies contain so few heavy elements compared to their larger counterparts. This mechanism also contributes to the broader understanding of why certain galaxies stop forming stars altogether, a key aspect of galaxy evolution. Beyond shaping galaxies, supernovae may also leave behind long-lasting cosmic footprints in unexpected places. Some researchers have proposed that supernova remnants could be linked to mysterious ultra-high-energy cosmic rays, the most energetic particles observed in nature. These particles, which travel at nearly the speed of light, bombard Earth constantly, yet their origins remain uncertain. If supernova remnants, particularly those involving young neutron stars or magnetars, are confirmed as sources of these extreme cosmic rays, it would provide a major breakthrough in high-energy astrophysics. On a more speculative front, some scientists have even explored the idea that supernovae could be used as natural astrophysical laboratories for testing the behavior of matter under conditions impossible to replicate on Earth. The immense pressures and temperatures inside an exploding star allow for nuclear reactions that go beyond what is possible in human-made particle accelerators. By studying the spectral signatures of elements produced in supernovae, physicists can refine models of nuclear fusion, helping to understand the forces that govern both stellar evolution and the nature of matter itself. Supernovae are also thought to play a role in the evolution of magnetic fields on cosmic scales. The powerful plasma flows generated by supernova explosions can twist and amplify magnetic fields within galaxies, potentially contributing to the large-scale magnetic structures observed in the Milky Way and beyond. Some theories suggest that repeated cycles of star formation, supernova explosions, and gas mixing over billions of years may have helped generate and sustain the magnetic fields that permeate entire galaxies. Another growing area of research is the study of failed supernovae, a rare but fascinating outcome where a massive star collapses into a black hole without producing a visible explosion. In these cases, rather than triggering a brilliant flash, the star simply disappears from view, leaving behind an event horizon from which no light can escape. If scientists can identify more examples of such disappearing stars, it would provide a new window into black hole formation and help constrain the limits of stellar collapse. The continued observation of supernovae across different wavelengths has also revealed surprises about their environments. In some cases, astronomers have detected strong X-ray and radio emissions from supernovae interacting with unexpectedly dense surroundings. These observations suggest that some massive stars undergo intense episodes of mass loss in the years or even months before they explode. This challenges traditional models of stellar death, which assume a more gradual evolution toward the final explosion. With the advent of next-generation space telescopes like the James Webb Space Telescope, JWST, astronomers are now capable of detecting the faint infrared signatures of supernovae in the early universe. This allows researchers to probe some of the very first stellar explosions that occurred after the Big Bang, providing a glimpse into how the first galaxies were enriched with heavy elements. Such studies are crucial for understanding the transition from the primordial universe, composed mostly of hydrogen and helium, to the complex, chemically rich cosmos we see today. In the coming decades, artificial intelligence and machine learning will play an even greater role in supernova research. AI-driven algorithms are already helping astronomers detect and classify supernovae in real time, sifting through vast amounts of sky survey data to identify new explosions as they happen. As technology advances, AI may even be able to predict supernovae before they occur by analyzing subtle changes in the brightness and behavior of massive stars. The potential for discovering entirely new types of stellar explosions remains high. Some theorists have proposed the existence of supernova imposters, events that resemble supernovae in brightness but do not completely destroy the star. These transient events, sometimes linked to massive eruptions in luminous blue variables, LBVs, highlight the diverse and still poorly understood ways in which stars can end their lives. Perhaps most exciting of all is the possibility of witnessing a nearby supernova in our lifetime. If a star like Betelgeuse were to explode, it would become one of the brightest objects in the night sky, visible even during the day. Such an event would provide an unprecedented opportunity for astronomers to study a supernova in exquisite detail, capturing its evolution from the first moments of collapse to the formation of its remnant. Given the unpredictability of stellar death, the next major supernova could happen at any time, in any galaxy, or even in our cosmic backyard. Supernovae remain one of the most powerful forces in the universe, shaping everything from the smallest particles to the grandest cosmic structures. They are the creators of elements, the sculptors of galaxies, and the engines of cosmic evolution. As our observational tools and theoretical models continue to improve, the mysteries of these stellar titans will gradually be unveiled, revealing even deeper connections between the life and death of stars and the unfolding story of the cosmos. Supernovae also hold the potential to reshape our understanding of time, space, and fundamental physics. Some of the most extreme supernovae, particularly those involving the formation of black holes, may generate exotic effects such as time dilation due to intense gravitational fields. Studying these events allows astrophysicists to test Einstein's general relativity in extreme conditions, pushing the boundaries of what we know about the nature of spacetime itself. One particularly fascinating aspect of supernovae is their ability to act as cosmic lighthouses for deep space exploration. The immense brightness of certain supernovae, particularly type Ia, allows astronomers to measure cosmic distances with remarkable accuracy. These standard candles have been instrumental in refining our understanding of the Hubble constant, which describes the expansion rate. However, recent measurements have revealed inconsistencies in the exact value of this constant, leading to the so-called Hubble tension. The discrepancy suggests that there may be unknown physics at play, possibly hinting at new forces or undiscovered properties of dark energy. The connection between supernovae and dark energy remains one of the greatest unsolved mysteries in cosmology. The discovery that the universe's expansion is accelerating, rather than slowing down, was made through careful observations of distant type Ia supernovae. These measurements revealed that a previously unknown force, now called dark energy, dominates the universe, driving galaxies apart at an ever-increasing rate. Understanding the precise nature of dark energy requires continuous refinement of supernova observations, pushing astronomers to discover ever more distant explosions at the very edges of the observable universe. Supernovae are also central to the search for extraterrestrial life. While their destructive power can be lethal to planets in close proximity, their role in spreading essential elements across galaxies makes them indispensable to the emergence of life. The balance between these two effects, the potential for devastation versus enrichment, plays a key role in determining which parts of the universe are most hospitable to life. Some researchers believe that the periodic occurrence of supernovae in the Milky Way may have influenced Earth's biosphere, triggering evolutionary leaps or even mass extinctions. Recent studies suggest that supernovae may have left signatures in Earth's geological record. For instance, layers of iron-60 isotopes found in ocean sediments indicate that nearby supernovae likely affected Earth's atmosphere within the past few million years. These cosmic events could have altered the planet's climate, increased radiation exposure, or even contributed to minor extinctions. Understanding how frequently such nearby explosions occur, and their potential impact on planetary systems, will help scientists assess the long-term habitability of Earth and exoplanets alike. Another tantalizing avenue of research is the potential role of supernovae in triggering planetary system formation. The shock waves from supernovae have been observed to compress gas clouds, setting off the collapse that leads to star and planet formation. Some scientists hypothesize that our own solar system may have formed in the aftermath of a nearby supernova. The presence of certain radioactive isotopes in meteorites supports this theory, suggesting that a supernova explosion may have seeded our early solar nebula with the heavy elements that would eventually form the Sun, Earth, and the other planets. From an observational standpoint, astronomers are constantly refining methods for detecting supernovae in the earliest moments of explosion. Recently, several shock breakout events, brief flashes of ultraviolet and X-ray radiation marking the first moments of a supernova, have been detected, providing crucial insights into the structure of dying stars before they explode. Catching these initial bursts in real time remains a major goal of modern astrophysics, as they provide a rare glimpse into the final instance of stellar collapse. Perhaps even more mind-bending is the possibility that some supernovae could produce exotic remnants beyond neutron stars and black holes. Some theorists have speculated about the existence of strange stars, composed of even more fundamental particles called strange quarks. These hypothetical objects would be more compact than neutron stars but not quite black holes, offering a new window into the behavior of matter under extreme pressures. The future of supernova research is incredibly promising. With the upcoming launch of advanced space telescopes and the continued expansion of ground-based surveys, astronomers will soon be able to study these cosmic events in greater detail than ever before. The Vera C. Rubin Observatory's LSST will revolutionize our ability to detect supernovae in near real time, while next-generation gravitational wave detectors may capture signals from core collapse events as they unfold. Combined with increasingly powerful supercomputers capable of simulating these explosions in 3 dimensions, the next decades promise to bring a new era of discoveries in supernova physics. As we continue to probe the universe, supernovae remain among the most important celestial events for understanding everything from stellar evolution to the fate of the cosmos. They are reminders that the universe is in a constant state of transformation, where the death of one star paves the way for the birth of new worlds. Whether they are forging the elements that build planets, shaping galaxies, or revealing the nature of dark energy, supernovae stand as cosmic sentinels of change, lighting the way for future exploration and discovery. Supernovae are among the most powerful and transformative events in the universe. They are both creators and destroyers, forging the elements necessary for life while also unleashing forces capable of reshaping entire galaxies. Their influence extends from the microscopic world of atoms to the vast cosmic structures that define the universe's evolution. From seeding planetary systems with essential materials to serving as beacons for measuring cosmic expansion, these stellar explosions connect the past, present, and future of the cosmos in profound ways. Despite centuries of study, supernovae continue to surprise us. Each new observation brings fresh insights, challenges existing theories, and deepens our understanding of the life cycle of stars. The mysteries surrounding these cataclysmic events, from their role in cosmic evolution to their potential connection with dark energy and extreme physics, ensure that they will remain a central focus of astronomical research for years to come. As our observational tools grow more advanced and our theoretical models more precise, we stand on the brink of a new era in supernova science. The next great explosion, whether in our galaxy or far beyond, may hold the key to answering some of the most profound questions about the universe. Until then, supernovae continue to serve as cosmic milestones, marking the endless cycle of birth, death, and renewal that has shaped the cosmos for billions of years, and will continue to do so for eons to come. The Sunflower Galaxy, designated Messier 63, M63, is a stunning spiral galaxy located approximately 29 million light-years away in the constellation Canes Venatici. It is part of the M51 group, a small collection of galaxies that includes the famous Whirlpool Galaxy, M51. M63 is known for its striking appearance, resembling the pattern of a sunflower, with tightly wound spiral arms that are filled with young, hot stars and dense dust lanes. This galaxy is classified as a flocculent spiral, meaning that instead of well-defined arms like those in grand design spirals, it has patchy and fragmented structures of star-forming regions. These bright regions are the result of intense stellar nurseries where gas and dust collapse under gravity to form new stars. The ultraviolet and infrared observations of M63 reveal ongoing star formation, with clusters of massive, short-lived stars illuminating the surrounding interstellar medium. One of the most fascinating aspects of M63 is its extended stellar halo, which contains faint streams of stars likely remnants of past galactic mergers. These stellar streams provide key insights into the history of galaxy formation and the interactions between galaxies over billions of years. Astronomers have used deep imaging techniques to uncover evidence of tidal disruptions, suggesting that M63 has consumed smaller satellite galaxies in the past. The central bulge of M63 harbors an active galactic nucleus, AGN, although it is relatively weak compared to more powerful quasars. The presence of a supermassive black hole at the core is inferred from X-ray emissions and the motions of stars near the center. This black hole, like those in many other spiral galaxies, plays a crucial role in regulating the galaxy's evolution through feedback mechanisms. M63 also exhibits a vast, faint outer disk that extends much farther than its bright central region. This extended disk structure is composed of older stars and contains a diffuse population of globular clusters. The disk's rotation has been mapped using radio observations of neutral hydrogen (Hi) gas, revealing the presence of dark matter that influences the galaxy's dynamics. The distribution of dark matter in M63 follows a pattern consistent with the predictions of cold dark matter cosmology, supporting the idea that galaxies are embedded in vast, unseen halos of dark matter. Additionally, the Sunflower Galaxy has been a target for studies of cosmic dust, as it contains significant amounts of interstellar material that absorbs and re-emits light at different wavelengths. Infrared telescopes, such as the Spitzer Space Telescope, have detected large reservoirs of dust within M63, which contribute to its overall energy balance. This dust plays a critical role in shielding molecular clouds from intense radiation, allowing them to collapse and form new stars. Observations with radio telescopes have also revealed that M63 possesses a diffuse, extended magnetic field. Magnetic fields in galaxies are still not fully understood, but they are believed to be linked to the motion of ionized gas and the rotational dynamics of the disk. These fields influence the behavior of cosmic rays and contribute to the complex interplay between interstellar matter and energetic particles. Despite its relatively calm appearance, M63 is an evolving system undergoing continuous changes driven by internal and external forces. The interplay between star formation, galactic mergers, and feedback from supernovae contributes to its long-term development. Understanding M63 helps astronomers refine models of galactic evolution and provides a glimpse into the fate of our own Milky Way, which shares some structural similarities with this cosmic sunflower. The study of M63 also contributes to the broader understanding of how spiral galaxies form and change over time. By comparing it to other galaxies in different stages of evolution, scientists can trace the processes that shape the universe on large scales. Each new observation brings additional details that refine our knowledge of the physical laws governing galaxy formation and cosmic structures. The outer regions of M63 provide a laboratory for studying the intergalactic medium, the vast expanse of tenuous gas that fills the space between galaxies. The interaction of this gas with the galactic halo influences the future growth of the galaxy. Some observations suggest that M63 might still be accreting material from its surroundings, slowly increasing in mass as it captures diffuse gas and small satellite galaxies. In addition to its scientific significance, M63 remains a favorite target for astrophotographers and amateur astronomers. Its relatively high surface brightness and distinctive structure make it an excellent object for observation with medium-sized telescopes. Through long-exposure imaging, even amateur astronomers can capture the intricate details of its spiral arms and glowing star-forming regions. As research on M63 continues, new technologies and more powerful telescopes, such as the James Webb Space Telescope, will provide even deeper insights into its composition, history, and the role it plays in the cosmic web. The Sunflower Galaxy, Messier 63, M63, is a celestial masterpiece that not only captivates the eyes but also offers a wealth of scientific intrigue. Situated approximately 29 million light-years away in the northern sky constellation of Canes Venatici, this spiral galaxy belongs to the M51 group, a family of galaxies dominated by the iconic Whirlpool Galaxy, M51. Though less famous than its larger counterpart, M63 exhibits a beauty of its own, with swirling, fragmented spiral arms filled with young stars, glowing nebulae, and dark, intricate dust lanes. Unlike grand design spirals, which feature well-defined and symmetrical arms, M63 is classified as a flocculent spiral. This means that its spiral arms appear more fragmented, resembling loose patches of star-forming regions rather than continuous, sweeping structures. The flocculent pattern is the result of self-propagating star formation, where clusters of new stars trigger the birth of subsequent generations of stars in a chain reaction. This leads to a chaotic yet mesmerizing appearance, much like the swirling pattern of sunflower petals that inspired its name. Infrared and ultraviolet observations reveal that M63 is an actively star-forming galaxy, with numerous stellar nurseries embedded in its spiral arms. These regions are filled with ionized hydrogen gas, HII regions, where newborn stars illuminate the surrounding clouds of dust and gas. The presence of large amounts of interstellar dust suggests that the galaxy has an ample supply of raw material for future star formation, ensuring its continued evolution. One of the most intriguing discoveries about M63 is the presence of stellar streams, faint, elongated structures surrounding the galaxy. These stellar streams are the remnants of smaller galaxies that M63 has gravitationally disrupted and absorbed over millions of years. This process, known as galactic cannibalism, is common in the universe, as larger galaxies grow by consuming their smaller neighbors. Deep imaging surveys have revealed a vast, diffuse halo of stars encircling M63, extending far beyond its visible disk. The halo is thought to contain traces of past mergers, including shredded remnants of ancient star clusters and dwarf galaxies that once orbited M63. By studying these streams, astronomers can reconstruct the galaxy's merger history and gain insights into the hierarchical formation of spiral galaxies. Interestingly, the presence of these streams suggests that M63 is still dynamically evolving. Some of the disrupted satellites may have introduced new elements into the galaxy, such as dark matter, a mysterious and invisible form of matter that influences the movement of stars. By mapping the motions of the stars in these streams, scientists can probe the dark matter distribution in M63, shedding light on one of the biggest mysteries in modern astrophysics. Like most large galaxies, M63 appears to be enshrouded in an extensive halo of dark matter that extends well beyond its luminous spiral arms. Dark matter does not emit or absorb light, making it invisible, but its presence is inferred through its gravitational effects on the galaxy's rotation. Observations using radio telescopes to map the distribution of neutral hydrogen gas, HI, in M63 reveal that the galaxy's outer disk rotates at a nearly constant speed, rather than slowing down as expected if only visible matter were present. This phenomenon, known as the galaxy rotation curve problem, provides compelling evidence for dark matter. Without dark matter, the outer stars of M63 would not have enough gravitational support to remain bound to the galaxy and would drift away into intergalactic space. Modern simulations suggest that M63, like many other spiral galaxies, resides within a massive dark matter halo that dictates its overall shape and motion. Understanding the properties of this dark matter halo is crucial for refining theories of galaxy formation and the nature of dark matter itself. At the core of M63 lies a supermassive black hole, SMBH, a common feature in most large galaxies, including the Milky Way. While not as active as the supermassive black holes in quasars or Seyfert galaxies, the black hole in M63 is detectable through its subtle influence on the motions of nearby stars and faint X-ray emissions. Although M63 does not exhibit the dramatic outbursts associated with highly active galactic nuclei, AGN, its central black hole likely plays a role in regulating star formation by heating and expelling gas from the galactic nucleus. This process, known as AGN feedback, can suppress excessive star formation and influence the long-term evolution of the galaxy. Beyond its visible structure, M63 also possesses an extended stellar disk that stretches far beyond the bright central regions. This outer disk is composed mostly of older stars and low-density gas, hinting at past interactions with other galaxies. Some observations suggest that this extended disk may still be accreting material from its surroundings, slowly increasing M63's mass over time. Another fascinating aspect of M63 is its magnetic field, which has been detected through radio observations. The role of magnetic fields in galaxy evolution is still not fully understood, but they are thought to influence the movement of interstellar gas, the formation of cosmic rays, and even the dynamics of spiral arms. In M63, the magnetic field appears to follow the contours of the spiral structure, guiding the flow of charged particles through the galaxy's disk. Infrared observations of M63 reveal that it contains vast amounts of cosmic dust, which absorbs and re-emits light at different wavelengths. This dust plays a crucial role in the galaxy's ecology, as it provides the raw material for new star formation and shields molecular clouds from harsh radiation. Observations from the Spitzer Space Telescope and the Herschel Space Observatory have detected cold dust reservoirs in M63, suggesting that it may continue forming stars for billions of years. Additionally, the infrared glow of the dust provides clues about the presence of organic molecules, known as polycyclic aromatic hydrocarbons, PAHs, which are thought to be among the building blocks of life. M63 is not an isolated entity but a part of a larger cosmic structure known as the M51 group. This group of galaxies, bound together by gravity, is a microcosm of the large-scale structure of the universe, where galaxies cluster together in vast filaments and cosmic webs. The interactions within this group may have shaped M63's evolution, influencing its spiral structure and triggering bursts of star formation. Studying M63 within the context of the cosmic web allows astronomers to understand how galaxies interact and evolve over billions of years. These studies help us place the Milky Way within a broader cosmic framework, revealing the dynamic processes that govern galaxy formation on all scales. M63 remains a popular target for both professional astronomers and amateur astrophotographers. Its relatively high surface brightness makes it accessible to backyard telescopes, and long-exposure photography reveals its intricate flocculent arms and star-forming regions. Advances in space telescopes and adaptive optics continue to unveil new details about this enigmatic galaxy, promising even more discoveries in the years to come. As technology advances, future observatories such as the James Webb Space Telescope, JWST, and next-generation radio telescopes will provide even deeper insights into M63's history, structure, and role in the cosmic evolution. Through these observations, we continue to unravel the mysteries of the Sunflower Galaxy, revealing the intricate dance of matter and energy that shapes our universe. M63's evolution is shaped by a complex interplay of internal processes and external influences, making it a fascinating subject for astronomers studying the life cycle of galaxies. The formation of stars within its spiral arms follows a rhythmic pattern governed by the density waves that sweep through the disk. These waves compress interstellar gas, triggering gravitational collapse and the birth of new stars in a cascading effect. The most massive of these stars, often forming in dense stellar clusters, live short but brilliant lives, producing intense ultraviolet radiation and powerful stellar winds before ending in supernova explosions. These supernovae, in turn, enrich the surrounding interstellar medium with heavy elements, seeding the next generation of stars and planetary systems. The continuous cycle of star formation and destruction not only fuels the galaxy's evolution but also helps shape its visible structure. The remnants of dead stars contribute to the formation of nebulae, creating intricate filaments of gas and dust that weave through the galaxy's arms. Some of these remnants form neutron stars or even black holes, which exert their own gravitational influence on the surrounding environment. As gas is recycled through supernova explosions and stellar winds, it slowly migrates toward the galactic center, where it may eventually feed the supermassive black hole lurking within the core of M63. The rotation of M63 presents another intriguing aspect of its nature. Unlike solid objects, galaxies do not rotate as a single unit, instead, their inner regions spin faster than the outer disk. This differential rotation stretches and distorts the spiral arms over time, giving them their characteristic appearance. The presence of dark matter is critical in maintaining the stability of this rotating structure, as the visible mass alone would not provide enough gravitational pull to hold the galaxy together. The detection of dark matter in M63's halo is consistent with similar findings in other spiral galaxies, reinforcing the idea that a vast, unseen component of the universe exerts an invisible but essential influence on galactic dynamics. Beyond the edges of the main disk, the galaxy's outskirts hold remnants of past interactions with smaller satellite galaxies. These faint tidal features, barely visible in optical wavelengths, suggest that M63 has undergone a series of minor mergers over the past several billion years. Such interactions are a key mechanism by which spiral galaxies grow and evolve, gradually accumulating mass and reshaping their structure. Some of the infalling material from these encounters may still be fueling star formation in M63's outer regions, contributing to its extended stellar disk. Observations in the radio spectrum provide additional insights into the galaxy's interstellar medium, revealing vast reservoirs of neutral hydrogen gas that extend far beyond the visible boundaries of the galaxy. This diffuse gas acts as a fuel reserve for future star formation, but it also interacts with the surrounding cosmic environment, exchanging material with intergalactic space. Some of this gas is likely being stripped away by the gravitational pull of nearby galaxies in the M51 group, hinting at a slow but ongoing exchange of matter between neighboring systems. Magnetic fields, though invisible to the human eye, play an important role in shaping M63's interstellar environment. These fields influence the movement of charged particles, guiding the flow of cosmic rays and affecting the distribution of interstellar gas. Observations using polarized radio waves have revealed that M63's magnetic field follows the contours of its spiral arms, suggesting that the process of star formation itself may help amplify and maintain these fields over time. The interaction between magnetic fields and cosmic rays remains an area of active research, with potential implications for understanding the conditions that influence galactic evolution on a fundamental level. As astronomers continue to study M63 across multiple wavelengths, from X-rays to radio waves, new details emerge about the galaxy's structure and history. High-energy observations have detected faint X-ray emissions near the galactic core, possibly linked to the central black hole or to compact remnants of massive stars scattered throughout the disk. Infrared studies have mapped the distribution of interstellar dust, revealing hidden pockets of star formation that remain obscured in visible light. Ultraviolet observations highlight regions of recent stellar birth, where young, hot stars radiate energy at high intensities, gradually shaping the surrounding interstellar medium. The placement of M63 within the cosmic web further emphasizes its connection to the broader universe. Galaxies are not isolated islands in space, they exist within vast, interconnected structures shaped by gravity and dark matter. M63's location within the M51 group suggests that it has experienced gravitational interactions in the past, and possibly continues to exchange material with its neighbors. These cosmic interactions influence the flow of gas into and out of the galaxy, affecting its ability to form new stars and altering its long-term evolution. Deep field imaging of M63's outer halo has also revealed a population of globular clusters orbiting the galaxy at great distances. These ancient clusters, composed of densely packed stars, are among the oldest structures in the universe, serving as relics of the early stages of galactic formation. The presence and distribution of globular clusters in M63 provide clues about the history of mergers and accretion events that have shaped the galaxy over billions of years. Some of these clusters may have originated outside M63, captured from smaller galaxies that were eventually absorbed into the larger spiral system. The future of M63 remains an open question, as galaxies are constantly evolving on cosmic timescales. Over the next few billion years, it is likely that M63 will continue to interact with the surrounding galaxies in its group, possibly merging with some of its smaller companions. Such mergers could trigger new bursts of star formation, reshaping the structure of the galaxy and potentially altering its classification. If M63 follows a path similar to that of the Milky Way, it may eventually undergo a major collision with another spiral galaxy, leading to a transformation into an elliptical galaxy as star formation slows and the internal structure settles into a more spheroidal shape. Advancements in observational technology, including the upcoming generation of space telescopes and ground-based observatories, will continue to provide new insights into M63's structure, composition, and evolution. By studying galaxies like M63 in exquisite detail, astronomers gain a deeper understanding of the fundamental processes that shape the universe, from the birth of stars to the interactions of dark matter and the large-scale structure of cosmic formations. Each new discovery adds another piece to the puzzle, revealing the intricate and dynamic nature of galaxies as they move through cosmic time. As M63 continues its journey through cosmic time, its fate is intertwined with the invisible forces that govern the universe. The vast dark matter halo that surrounds the galaxy exerts a subtle but persistent gravitational influence, holding the outer stars in their orbits and shaping the motion of interstellar gas. The dark matter itself remains an enigma, yet its role in stabilizing the galaxy's structure is undeniable. Theories suggest that these halos formed early in the universe's history, serving as gravitational wells that attracted ordinary matter and provided the foundation for the formation of galaxies like M63. The study of M63's motion relative to other galaxies in the M51 group offers insight into its future trajectory. Astronomers have mapped the velocities of stars and gas within the galaxy, revealing patterns that suggest past gravitational interactions with nearby systems. Though M63 appears relatively undisturbed compared to the more dramatic encounters seen in some galaxies, faint distortions in its outer disk hint at subtle interactions over billions of years. It is possible that M63 is slowly drifting toward a larger-scale merger, a process that could reshape its structure over the course of cosmic time. Star formation within M63 is not uniform across its disk. Certain regions are far more active than others. These variations arise from differences in gas density, local gravitational effects, and the presence of shock waves triggered by supernovae. Some parts of the galaxy host massive stellar clusters where young, hot stars are packed tightly together, emitting powerful radiation that sculpts the surrounding clouds of gas and dust. In other regions, particularly the outer disk, star formation is much more gradual, with lower-mass stars forming in a more diffuse environment. Supernova explosions play a crucial role in redistributing heavy elements throughout M63. When massive stars reach the end of their lives, they collapse under their own gravity, releasing an immense burst of energy that sends shock waves rippling through the interstellar medium. These explosions not only enrich the galaxy with essential elements like carbon, oxygen, and iron but also generate turbulent motions in the gas, influencing the formation of new stars. Some of this material is ejected into intergalactic space, contributing to the diffuse medium that fills the cosmic web. The presence of high-energy cosmic rays within M63 further underscores the dynamic nature of its environment. These charged particles travel at nearly the speed of light, spiraling along magnetic field lines and interacting with interstellar matter. The origins of cosmic rays in M63 are linked to supernovae and the energetic processes occurring near the galactic nucleus. As these particles propagate through the galaxy, they affect the chemistry of interstellar clouds and may even play a role in regulating the formation of new stars. M63's spiral arms serve as natural laboratories for studying the interplay between gravity, star formation, and interstellar turbulence. Unlike the well-organized arms seen in grand design spirals, M63's fragmented flocculent structure suggests that the star formation process is more chaotic and self-propagating. Instead of being driven by large-scale density waves, star formation in M63 likely occurs in localized bursts, triggered by interactions between molecular clouds. This leads to a patchy distribution of bright stellar nurseries, with some regions experiencing rapid bursts of formation while others remain relatively dormant. Observations at millimeter wavelengths have revealed that M63 contains significant reservoirs of cold molecular gas, the raw material for future star formation. This gas is concentrated along the spiral arms but extends into the outer regions of the galaxy as well. In some areas, the gas appears to be clumping together, forming the early stages of new star clusters. The presence of this cold gas suggests that M63 is still actively growing, gradually accumulating material from its surroundings and incorporating it into new generations of stars. The galactic nucleus of M63 remains a focal point for research, as it may hold clues about the past activity of its central black hole. While M63 is not classified as a strongly active galaxy, subtle signs of past activity can be detected in its core. Faint X-ray emissions and variations in the motion of nearby stars suggest that the supermassive black hole at the center may have experienced periods of increased activity in the past. It is possible that the black hole is currently in a dormant phase, awaiting new infalling material that could reignite its accretion process and trigger bursts of energetic radiation. Surrounding the central region, the inner disk of M63 exhibits a complex interplay of old and young stars. The presence of older, redder stars suggests that this region has undergone multiple cycles of star formation over billions of years, while the occasional appearance of young, blue stars indicates that new stars continue to form even in the galaxy's inner regions. The balance between old and young stars provides insight into the long-term evolutionary history of M63, offering clues about the processes that have shaped its structure over cosmic time. In the farthest reaches of M63, beyond the visible spiral arms, lies a diffuse stellar halo that extends well into intergalactic space. This halo is composed of ancient stars and globular clusters, remnants of the galaxy's early formation history. The distribution of these old stars suggests that M63 has undergone multiple mergers and accretion events, gradually incorporating smaller satellite galaxies into its structure. Some of these stars may have originated in other galaxies before being captured by M63's gravitational field, forming a scattered population of intergalactic wanderers. The future of M63 will likely be shaped by its interactions with the broader M51 group. While no major collisions are imminent, gravitational influences from neighboring galaxies could gradually alter its structure over time. In the distant future, M63 may experience a significant merger event, potentially leading to a transformation into a different type of galaxy. If it eventually collides with another spiral galaxy, the resulting merger could trigger a burst of star formation, creating new stellar populations and reshaping the galaxy into an elliptical or lenticular form. As telescopes and observational techniques continue to improve, new discoveries about M63 will further refine our understanding of its nature and evolution. The James Webb Space Telescope and next-generation radio observatories will provide deeper insights into the galaxy's composition, revealing details about its gas dynamics, star formation history, and the influence of its central black hole. Each new piece of data adds to the broader picture of how galaxies evolve over billions of years, offering a glimpse into the past and future of the universe itself. The intricate dance of matter and energy within M63 continues to unfold across vast cosmic timescales, driven by gravitational forces, star formation cycles, and intergalactic interactions. As new stars are born in the dense molecular clouds of the spiral arms, they ignite nuclear fusion, producing intense radiation that shapes the surrounding environment. The most massive of these stars burn through their fuel in mere millions of years, their powerful stellar winds dispersing gas and dust while enriching the galaxy with heavy elements. These elements, forged in the hearts of dying stars, will one day form the building blocks of new planetary systems, perhaps even ones capable of sustaining life. The stellar populations within M63 reflect the complex history of the galaxy, with older, metal-poor stars residing in the extended halo and younger, metal-rich stars concentrated in the inner regions. The distribution of these stars provides a timeline of the galaxy's formation, revealing periods of rapid growth interspersed with quieter phases of evolution. The study of these populations allows astronomers to reconstruct the past interactions that have shaped M63, from early mergers with dwarf galaxies to more recent episodes of internal star formation. The motion of stars within the galaxy follows intricate patterns dictated by gravity and dark matter. In the inner regions, stars orbit the galactic center at high velocities, forming a dense, rotating disk. Further out, in the extended stellar halo, individual stars follow elongated orbits, some of which suggest they were once part of smaller galaxies that were absorbed by M63. These orbits provide crucial evidence for the hierarchical nature of galaxy formation, in which larger galaxies gradually consume smaller companions over billions of years. Gas dynamics within M63 reveal additional layers of complexity. Hydrogen gas, the primary fuel for star formation, is distributed unevenly throughout the galaxy, with dense concentrations in the spiral arms and more diffuse regions in the outer disk. The interplay between gravity, magnetic fields, and stellar radiation shapes the movement of this gas, influencing where new stars will form. Observations in the radio spectrum have uncovered extended structures of neutral hydrogen, some of which appear to be remnants of past interactions with other galaxies. The influence of the supermassive black hole at the center of M63 remains the subject of ongoing research. While the black hole is not currently in an active feeding phase, there are signs that it has influenced the surrounding stars and gas over long timescales. Occasional bursts of activity, possibly triggered by the infall of material from the inner disk, may produce high-energy radiation detectable in X-rays. These emissions offer a glimpse into the processes occurring near the event horizon, where the immense gravitational pull of the black hole warps space and time. Beyond the visible structure of M63 lies its vast, unseen dark matter halo, an enigmatic component that dominates the galaxy's total mass. The gravitational effects of this halo extend far beyond the luminous disk, shaping the rotation curve of the galaxy and providing the necessary mass to hold its structure together. The exact nature of dark matter remains one of the greatest mysteries in modern astrophysics, but its influence on galaxies like M63 is undeniable. By studying how stars and gas move within the galaxy, astronomers can infer the distribution of this invisible mass and refine theoretical models of the universe. The intergalactic environment surrounding M63 is also a key factor in its evolution. As part of the M51 group, the galaxy exists within a dynamic system where gravitational interactions with neighboring galaxies can influence its shape and motion. Tidal forces from these interactions may induce subtle distortions in the outer disk, triggering waves of star formation or stripping away loosely bound material. In some cases, these interactions can lead to the formation of faint tidal streams, elongated structures of stars and gas that trace the remnants of past encounters. The extended halo of M63 contains additional clues about the galaxy's past. Deep imaging surveys have revealed faint stellar streams that may be the remnants of ancient mergers. These structures are difficult to detect in visible light but can be traced using infrared and radio observations. The presence of these streams suggests that M63 has undergone multiple phases of growth, gradually accumulating mass over billions of years through the accretion of smaller galaxies. At the periphery of M63, globular clusters orbit the galaxy in a vast, diffuse swarm. These dense collections of ancient stars are among the oldest objects in the universe, serving as relics from the early epochs of galaxy formation. The number and distribution of globular clusters in M63 provide insight into the processes that shaped the galaxy, as well as the role of dark matter in organizing its large-scale structure. Some of these clusters may have originated within M63 itself, while others could have been captured from disrupted satellite galaxies. As technology advances, future telescopes will reveal even more about M63's composition and history. The upcoming generation of observatories, including the Extremely Large Telescope (ELT), and the next wave of space-based infrared missions, will allow astronomers to probe the galaxy's structure in unprecedented detail. These instruments will provide deeper insights into the formation of spiral arms, the properties of the interstellar medium, and the interactions between stars, gas, and dark matter. The long-term fate of M63 will likely be determined by its interactions with the M51 group and its gradual evolution as a spiral galaxy. Over the next several billion years, it may experience further mergers with smaller galaxies, altering its structure and triggering new waves of star formation. If it eventually merges with a galaxy of similar size, it could undergo a transformation into a more elliptical shape, a fate predicted for many spiral galaxies in dense galactic environments. Even in its current form, M63 remains a breathtaking example of the diversity of galactic structures found throughout the universe. Its intricate flocculent arms, vast reservoirs of interstellar gas, and enigmatic dark matter halo all contribute to its ongoing evolution. The processes shaping M63 are not unique to this galaxy but are representative of the broader mechanisms driving the growth and transformation of galaxies across cosmic time. As the light from M63 continues to travel across millions of light-years to reach Earth, it carries with it the story of a galaxy in motion, a dynamic, evolving system shaped by gravity, star formation, and the unseen forces that govern the cosmos. Each new observation adds another chapter to this story, bringing us closer to understanding the intricate and beautiful complexity of the universe. The journey of M63 through cosmic time is marked by an ever-evolving interplay of forces, from the gravitational dance of stars to the subtle but profound influence of dark matter. Each layer of the galaxy tells a different story, encoded in the motions of its stars, the chemistry of its gas, and the radiation it emits across the electromagnetic spectrum. Observing M63 is like looking back in time, as the light reaching us today left the galaxy nearly 30 million years ago, offering a snapshot of its past while it continues to evolve in ways we can only predict. Deep within the spiral arms, the cycle of stellar birth and death continues unabated. Young stars illuminate their surroundings, their intense ultraviolet radiation carving out glowing cavities in the interstellar medium. The pressure waves from these massive stars push gas into new pockets of compression, triggering the next generation of star formation. Over time, as these stars exhaust their fuel, they explode in supernovae, dispersing heavy elements and driving shockwaves through the galaxy's disk. These supernova remnants create turbulence in the interstellar medium, stirring up clouds of gas and preventing them from collapsing too quickly into new stars, thus regulating the pace of stellar formation. The flocculent nature of M63's arms suggests that its star formation is more sporadic than in grand design spirals, where density waves create a more uniform pattern of stellar birth. Instead, M63's structure arises from a self-propagating process, where individual regions ignite in bursts before fading as the local gas supply is depleted. This patchy, dynamic process makes M63 an excellent laboratory for studying how spiral galaxies sustain star formation over long timescales without the need for a strong central bar or a well-defined density wave pattern. The outer disk of M63 extends far beyond what is visible in optical wavelengths, containing vast reservoirs of neutral hydrogen gas. This gas, mapped in detail by radio telescopes, provides a glimpse into the long-term future of the galaxy. If left undisturbed, this outer gas could fuel star formation for billions of years, gradually replenishing the supply of new stars as the inner regions continue their evolutionary processes. However, the presence of neighboring galaxies in the M51 group suggests that interactions may disrupt this extended disk over time, pulling gas away through tidal interactions or funneling it inward to fuel bursts of new star formation. Beyond the main stellar disk, the halo of M63 contains relics of past galactic mergers. These include faint stellar streams, remnants of smaller galaxies that were once gravitationally captured and slowly torn apart by tidal forces. These streams, barely detectable in visible light, have been revealed through deep imaging and infrared observations. Their presence confirms that M63, like most large galaxies, has not formed in isolation but has grown through a series of accretion events, absorbing smaller satellite galaxies over billions of years. Among the most ancient structures within this halo are M63's globular clusters, densely packed spheres of old stars that orbit far from the galaxy's bright spiral arms. These clusters, often containing some of the oldest known stars, serve as fossil records of M63's early history, dating back to the era when the galaxy first formed. Some of these globular clusters may have originated within M63 itself, while others were likely captured from merging dwarf galaxies, becoming permanent residents of the growing system. The magnetic field of M63, though invisible to the eye, weaves through the galaxy, influencing the motion of charged particles and shaping the structure of the interstellar medium. Observations in polarized radio wavelengths have revealed that this field follows the contours of the spiral arms, suggesting a close link between star formation and magnetic activity. Magnetic fields play a crucial role in regulating the collapse of interstellar gas clouds, providing resistance against gravitational collapse in some regions while channeling material into dense star-forming filaments in others. The exact mechanisms behind the maintenance of galactic magnetic fields remain an active area of research, but M63 provides an excellent testbed for studying these elusive forces. As M63 moves through space, its interactions with the cosmic web, the large-scale structure of the universe, continue to shape its fate. The inflow of gas from the intergalactic medium, though difficult to detect directly, may provide a steady trickle of new material that fuels ongoing star formation. At the same time, interactions with the hot plasma that permeates galaxy groups could strip away some of this gas, limiting the galaxy's ability to sustain its current level of activity indefinitely. These competing processes, known as accretion and ram pressure stripping, determine whether M63 will continue to grow or slowly fade as its gas supply is depleted. In the distant future, M63's evolution will likely be dominated by gravitational interactions within the M51 group. The possibility of a future merger remains open, as galaxies within groups and clusters are bound by gravity and can gradually drift toward one another over billions of years. If M63 eventually merges with another spiral galaxy, the resulting collision could trigger a dramatic transformation, leading to a burst of star formation followed by a gradual settling into a more elliptical shape. Such mergers are a common fate for spiral galaxies and are thought to be the ultimate destiny of our own Milky Way when it eventually collides with the Andromeda Galaxy. The study of M63 extends beyond understanding a single galaxy. It provides a window into the universal processes that govern galaxy formation and evolution. Each new observation, whether in visible light, infrared, radio waves, or X-rays, adds another piece to the puzzle, revealing the intricate interactions that shape galaxies over billions of years. The James Webb Space Telescope and future observatories will bring even greater clarity to these studies, allowing astronomers to peer deeper into M63's structure and uncover the fine details of its composition. As M63 continues its cosmic journey, the forces at play within and around it ensure that it remains a dynamic, evolving system. The light we see today is a mere moment in its long history, and the processes that govern its transformation will continue long after our time. By studying galaxies like M63, we not only deepen our understanding of the universe but also gain perspective on our own place within it, as inhabitants of a similarly evolving spiral galaxy, part of the same grand cosmic story. The ongoing transformation of M63 is a testament to the continuous, dynamic processes that govern the evolution of galaxies. Even in its current state, appearing relatively stable, the galaxy is far from static. It is an intricate system in motion, where every star, gas cloud, and dark matter halo contributes to a vast, interwoven history stretching back billions of years and extending far into the future. Within its spiral arms, regions of intense star formation act as cosmic factories, forging new generations of stars from interstellar gas and dust. The interplay of gravity and pressure within these dense clouds leads to the birth of stars, some of which form in massive clusters, while others emerge in isolation. The ultraviolet light from the most massive stars ionizes the surrounding gas, creating vast glowing nebulae that radiate in optical and infrared wavelengths. These luminous regions highlight the most active pockets of stellar birth, revealing the ongoing processes shaping the structure of M63. The presence of dust within M63 plays a crucial role in regulating star formation. While often seen as an obscuring factor in visible light observations, dust serves as a protective shield for the delicate molecular clouds where stars are born. It absorbs and scatters high-energy radiation, allowing cooler regions to remain stable long enough for gravity to trigger star formation. In infrared wavelengths, this dust glows with thermal radiation, allowing astronomers to map its distribution and trace the hidden networks of gas that fuel the galaxy's growth. As stars progress through their life cycles, they enrich the interstellar medium with heavier elements, essential for the formation of planets, moons, and potentially life-bearing environments. The remnants of past supernovae spread elements such as carbon, oxygen, and iron across the galaxy, gradually increasing its metallicity over time. This chemical evolution is evident in the varying compositions of stars throughout M63, with older stars in the halo exhibiting lower metallicity, while younger stars in the disk contain a higher abundance of heavy elements. By studying this chemical diversity, astronomers can reconstruct the star formation history of the galaxy and identify the epochs during which it experienced the most significant growth. The motion of stars within M63 provides additional insights into its evolution. Precise measurements of stellar velocities reveal patterns that indicate past gravitational interactions, either with unseen satellite galaxies or through internal processes such as spiral density waves. These waves, though less structured than in grand design spirals, influence the movement of gas and stars, helping to maintain the overall spiral pattern despite the galaxy's flocculent nature. In some regions, differential rotation stretches and distorts these patterns over time, creating the complex and fragmented appearance that characterizes M63. In the outskirts of the galaxy, beyond the bright central disk, lies an extended population of stars and globular clusters that trace the remnants of past mergers. These ancient stellar structures, some orbiting at great distances from the galactic core, are key indicators of M63's long-term growth. The presence of diffuse stellar streams suggests that smaller galaxies have been absorbed into M63's structure, leaving behind ghostly trails of stars slowly blending into the larger system. Future observations with ultra-sensitive telescopes may uncover even more of these structures, revealing a deeper record of the galaxy's past interactions. The dark matter halo enveloping M63 is perhaps its most enigmatic feature. Though invisible, its gravitational effects are undeniable, shaping the galaxy's rotation and influencing the motion of stars and gas. The exact nature of dark matter remains one of the most significant unsolved mysteries in astrophysics, but its role in stabilizing galaxies like M63 is well established. Without dark matter, the outer stars of the galaxy would be moving too fast to remain bound, and the entire structure would fly apart over cosmic timescales. The distribution and density of dark matter in M63 are inferred from rotation curves, which show a constant velocity far beyond where the visible mass should provide gravitational support. This suggests that a massive, unseen component surrounds the galaxy, extending well beyond its luminous disk. Beyond M63 itself, the intergalactic medium, the vast expanse of space between galaxies, plays a role in shaping its long-term evolution. The diffuse gas that permeates this medium may slowly accrete onto the galaxy, adding fresh material that could sustain future star formation. At the same time, gravitational interactions with neighboring galaxies in the M51 group could strip away some of M63's outer gas, limiting its ability to grow. These processes, though slow on human timescales, are fundamental to the life cycle of galaxies and influence their morphology over billions of years. The large-scale structure of the universe, in which galaxies are arranged in filaments and clusters, provides a broader context for M63's existence. As part of the cosmic web, M63 is not an isolated entity but rather a component of a much larger interconnected network. The forces that shaped it, early cosmic expansion, density fluctuations in the primordial universe, and the gradual accumulation of matter, are the same forces that govern the evolution of galaxies throughout the cosmos. Understanding M63 helps astronomers refine models of galaxy formation and evolution, offering clues about how structures in the universe develop and change over time. The future of M63 remains uncertain, though its trajectory will likely follow a path common to many spiral galaxies. Over the next few billion years, it may continue to accrete smaller galaxies, growing in mass and complexity. Eventually, as part of the natural life cycle of spiral galaxies, it could experience a significant merger, potentially with another large galaxy within its group. Such an event would trigger a transformation, disrupting the spiral structure and leading to the formation of a more spheroidal system. If this occurs, M63 may transition into a lenticular or elliptical galaxy, gradually consuming its remaining gas and settling into a quieter phase of evolution. Observations of M63 continue to push the boundaries of what we know about spiral galaxies. With each new technological advancement, astronomers uncover more details about its composition, motion, and interaction with the cosmic environment. The James Webb Space Telescope and future radio and infrared observatories will allow deeper studies of the galaxy's dust, gas, and stellar populations, revealing hidden structures and processes that remain invisible to current instruments. Despite the immense scales involved, the study of galaxies like M63 provides a bridge between the cosmic and the personal. The same physical laws that govern the motion of its stars also apply to our own Milky Way, reminding us that our galaxy is part of the same vast, interconnected universe. By looking outward and studying the distant light of M63, we gain a greater understanding of the fundamental forces that shape not just galaxies, but the very nature of existence itself. As M63 continues its cosmic journey, shaped by the interplay of gravity, dark matter, and the relentless cycle of star formation, it serves as a living testament to the dynamic nature of galaxies. Though millions of light-years away, its evolution mirrors the processes that have shaped countless other galaxies, including our own Milky Way. Every burst of star formation, every supernova explosion, and every subtle gravitational interaction contribute to an intricate cosmic dance that unfolds across billions of years. While its future remains unwritten, the forces at play ensure that M63 will not remain unchanged. Whether through gradual accretion of intergalactic material, interactions with neighboring galaxies, or even an eventual merger that reshapes its very structure, the Sunflower Galaxy will continue to evolve, much like all celestial bodies in the vast and ever-expanding universe. Its story, though still unfolding, is a reminder of the continuous cycle of creation and transformation that governs the cosmos. For astronomers, M63 remains a rich source of knowledge and inspiration, a window into the processes that define the life cycles of galaxies. As technology advances and our ability to observe the universe deepens, new discoveries about this fascinating galaxy will emerge, refining our understanding of the intricate forces that shape the universe. Though our time in the cosmos is fleeting, the light from M63 will continue to shine across the depths of space, a distant yet enduring beacon in the grand cosmic tapestry.
IC 1101, a colossal elliptical galaxy in the Virgo constellation, ranks among the largest known in the universe. Its immense diameter exceeds 6 million light-years, dwarfing the Milky Way, which spans approximately 100,000 light-years, located at the core of the Abell 2029 galaxy cluster. This cosmic behemoth stands out due to its sheer mass and unique characteristics. At its center lies a supermassive black hole, estimated to exceed 40 billion solar masses, exerting a profound influence on its structure and the surrounding cosmic environment. This titan of the cosmos is classified as a cannibal galaxy, having merged with numerous smaller systems over billions of years. These relentless mergers have shaped its elliptical form and led to the near cessation of star formation. Most of its stellar population is over 10 billion years old, giving the system a distinct yellowish hue. The absence of cold gas prevents new stars from forming, while its hot ionized material emits X-rays detectable by space observatories such as Chandra and XMM Newton. The massive halo surrounding this galactic colossus extends well beyond its visible boundaries, composed of stars, gas, and dark matter. It also contains intracluster light, a faint glow produced by stars ejected during past collisions. These remnants serve as a testament to the violent interactions that have shaped this celestial leviathan over cosmic time, ensuring its continued evolution within the vast Abell 2029 cluster. The study of this stellar giant and its counterparts provides invaluable insights into the formation and evolution of galaxies on a grand scale. As one of the most massive and luminous systems in the observable universe, it challenges our understanding of galactic growth. The role of environment, dark matter, and supermassive black holes in shaping such extraordinary structures remains a central focus of contemporary astrophysics. Often referred to as the Titan of Galaxies, this ancient behemoth continues to inspire awe, prompting further exploration into the mysteries of the cosmos. Situated in the dense environment of the Abell 2029 cluster, this colossal system serves as a natural laboratory for studying the interplay between galaxies and their surroundings. The cluster's intracluster medium, a hot, X-ray emitting plasma, interacts with the giant elliptical, influencing its evolution and that of its satellite galaxies. Gas stripped from smaller neighbors through ram pressure interactions enriches the medium, contributing to the overall complexity of the system. These processes highlight the dynamic nature of galaxy clusters, where gravitational forces and high-energy phenomena shape the universe on vast scales. Beyond its scientific significance, this cosmic monarch serves as a reminder of the diversity and scale of the universe. Its immense size, brilliance, and central location within the Abell 2029 cluster make it a prominent cosmic landmark, a beacon of light visible across hundreds of millions of light years. Observing this galactic titan provides a glimpse into the distant past, offering insights into the intricate interplay of forces that have shaped the cosmos. As research progresses, this ancient colossus and its analogues will remain pivotal to our quest for understanding the universe, offering a window into its boundless possibilities. The giant elliptical of Abell 2029 continues to intrigue astronomers with its sheer scale and complex history. This celestial titan, alternatively called the Abell 2029 core galaxy, stands as a testament to the immense forces at play in the universe. Measuring over 6 million light-years across, it dominates its galactic cluster in both size and influence, earning titles such as the Colossus of Virgo in astronomical discussions. This supergiant has undergone countless mergers, consuming smaller galaxies in a process that has shaped its current structure. Each interaction has added stars and gas, further enriching the galactic core. This relentless process, known as galactic cannibalism, underscores the dynamic interactions within dense cosmic environments. At its heart lies a supermassive black hole of extraordinary proportions, sometimes referred to as the gravitational anchor of Abell 2029. With a mass surpassing 40 billion suns, it is among the largest ever detected, governing the motions of stars and gas within the galaxy, while exerting influence on the broader cluster environment. The intense gravitational field of this singularity contributes to the galaxy's luminous core, radiating across vast distances, earning it epithets such as the light beacon of Virgo. The stellar population of this ancient colossus is predominantly old and yellowish, characteristic of elliptical galaxies. Most stars within this vast system exceed 10 billion years in age, marking a galaxy that has long since exhausted its supply of cold gas necessary for star formation. Instead, the stellar graveyard of Abell 2029 glows faintly with a golden hue, a visual indicator of its advanced evolutionary stage. Surrounding this interstellar monarch is a vast halo of dark matter and interstellar material, often termed the cosmic veil of Abell 2029, extending far beyond its visible boundaries. This halo influences the cluster's gravitational dynamics. Within it, intracluster light, a faint glow from stars stripped from their original galaxies, adds an ethereal quality to the region. These orphan stars, drifting through the intergalactic sea, serve as evidence of the violent history of galactic interactions that have defined the Abell 2029 monarch. The surrounding environment of this galactic elder is rich with X-ray emissions, a consequence of the hot plasma filling the Abell 2029 cluster. These high-energy phenomena, observable by Chandra and XMM Newton, reveal the turbulent conditions within the X-ray furnace of this dense system. Interactions with the cluster's tidal forces strip gas from smaller galaxies, enriching the intracluster medium and fueling the ongoing evolution of this cosmic giant. Studying this luminous elder of the universe provides unparalleled insights into galaxy formation and evolution. As one of the largest known galactic structures, it serves as a crucial subject for exploring extreme cosmic phenomena. The role of supermassive black holes, dark matter, and galactic mergers in shaping such immense systems remains a fundamental question in astrophysics, with the Colossus of Abell 2029 offering valuable clues. Despite its age and apparent dormancy in star formation, this golden leviathan continues to exert significant influence on its surroundings. Its gravitational pull dictates the movements of satellite galaxies and contributes to the broader dynamics of the Abell 2029 cluster. As the gravitational heart of Virgo, this celestial giant exemplifies the scale and power of cosmic structures, a reminder of the vast forces governing the universe. This eternal sentinel of the Virgo supercluster, sometimes referred to as the cosmic giant, stands as a silent witness to nearly the entire history of the universe. With an unfathomable size, this ancient behemoth has absorbed and consumed countless smaller galaxies, preserving a vast record of cosmic evolution within its structure. At its core lies a supermassive black hole of unimaginable scale, often described as the Abyssal King or the Dark Heart of Abell 2029. With a mass exceeding 40 billion suns, its gravitational pull is so intense that even light struggles to escape. The energy released by matter spiraling into this behemoth generates a luminous halo of X-rays, an eerie beacon that signals its presence across intergalactic space. This singularity, the cosmic anchor, dictates the structure of its host galaxy, binding stars and dark matter in an unending gravitational dance. The luminous behemoth stands as a monument to galactic cannibalism, a relentless cosmic predator. Over billions of years, it has consumed not just a few, but potentially thousands of smaller galaxies, merging their stars, gas, and dark matter into its sprawling form. These ancient collisions, some violent and others gradual, have left imprints across its vast halo, a graveyard of shattered galactic identities. Each merger has been a step toward its immense scale, making it one of the largest galaxies ever observed. Often described as the universal apex, it represents the ultimate fate of many evolving galaxies. Despite its outward stillness, this silent monarch is far from dormant. While its visible light radiates a golden hue, a testament to its aging stellar population, its hidden layers remain active. X-ray telescopes reveal a sea of hot plasma permeating the intracluster medium, a cauldron of gas stripped from neighboring galaxies via gravitational interactions. This invisible fire glows in high-energy wavelengths, exposing the turbulent forces shaping the Abell 2029 cluster. The galaxy's cosmic shroud, an immense halo extending beyond its core, envelops countless orphan stars. These unbound celestial wanderers drift aimlessly through the cluster, their faint collective glow known as intracluster light, preserving the story of ancient galactic violence and ongoing cosmic evolution. Here, in the interplay of light and shadow, lie countless mergers, some unfolding over millions of years, others in cataclysmic bursts. Yet, It is not only its scale that makes this stellar colossus remarkable, it challenges fundamental understandings of the universe itself. How did such a massive structure form? What are the limits of galactic growth? These unanswered questions push astronomers to look deeper into the void, searching for clues within the glow of this cosmic elder. Its existence serves as a reminder that, despite its apparent stillness, the universe is an ever-evolving place of energy, motion, and transformation. The role of dark matter in shaping this cosmic sovereign cannot be overstated. Without this enigmatic, unseen force, its vast mass would not remain intact. Scientists theorize that this dark empire of the cosmos is encased in a titanic dark matter halo, stretching far beyond its luminous boundaries. This invisible structure not only binds its stars together, but also dictates the motion of galaxies within the Abell 2029 cluster. Studying dark matter in such a monumental system provides essential insights into the forces that govern the universe on the largest scales. Perhaps most hauntingly, this eternal giant offers a glimpse into the ultimate fate of galaxies like our own. Over billions of years, as galaxies collide and merge, they gradually lose their distinct forms, their spirals fading into smooth, featureless ellipses filled with aging stars. In this way, the timeless Leviathan serves as a harbinger of cosmic inevitability, offering a vision of what the Milky Way and its neighbors may one day become. Yet, despite its dominance, even this galactic juggernaut is not eternal. The universe's expansion will eventually isolate it, as neighboring galaxies recede beyond the observable horizon. Trapped in an ever-growing void, this universal colossus will gradually dim, its stars burning out, leaving behind a cold, dark remnant. But for now, it remains a beacon of knowledge, a living relic of the universe's tumultuous past. The ancient monarch of Abell 2029, one of the grandest elliptical galaxies ever discovered, is more than a single entity. It is a microcosm of cosmic history. Every star within its vast expanse, every faint whisper of gas, every drifting shadow of dark matter holds a story spanning billions of years. This stellar labyrinth challenges our perceptions of time and space, inviting us to unravel its secrets, while reminding us of the universe's boundless complexity. The sheer magnitude of this galactic behemoth, sometimes called the infinite tapestry of Virgo, places it in a class of its own. Spanning over 6 million light-years in diameter, it could only have formed in one of the densest and oldest galactic environments. The Abell 2029 cluster, a gravitational cauldron housing thousands of galaxies, provided the ideal conditions for such a titan to emerge, often referred to as the cosmic overlord. This dominant force at the cluster's core sculpts the motions of stars, gas, and galaxies across millions of light-years. At its center lies its most mysterious and formidable feature, a supermassive black hole of unimaginable scale, sometimes called the cosmic abyss. This gravitational leviathan is not merely a point of intense mass, it is a dynamic engine, consuming matter and unleashing vast amounts of energy through radiation and relativistic jets. These jets, stretching for hundreds of thousands of light-years, act as cosmic lighthouses, visible across intergalactic distances. They also reshape the surrounding environment, heating nearby gas and preventing it from cooling into new stars. The intricate relationship between this dark heart and its host galaxy is one of the many puzzles astronomers seek to unravel. The Virgo colossus, with its ancient history and staggering scale, continues to intrigue scientists, offering a glimpse into the most extreme conditions the cosmos can produce. Every observation of this celestial titan deepens our understanding of the vast and evolving universe, reinforcing its place as one of the greatest galactic wonders ever discovered. This galaxy, sometimes poetically called the eternal jewel of the universe, stands as a relic of a bygone era, a testament to the cycle of galactic life and death across cosmic timescales. Its stars, predominantly ancient, resemble the dim embers of once bright stellar populations, collectively known as the Golden Veil of Abell 2029. These aging stars give the system its characteristic yellowish hue. The absence of young, blue stars confirms that star formation within this stellar mausoleum ceased long ago, leaving behind a tranquil but enduring celestial giant. Yet, for all its apparent serenity, this universal titan bears visible scars of its violent past, faint trails of intracluster light, drifting remnants of past galactic collisions, surround it like ghostly echoes of long-lost galaxies. These orphan stars, stripped from their original homes, now drift aimlessly in the gravitational tides of the cluster. Observing this cosmic haze allows astronomers to reconstruct the history of mergers that have fed this stellar behemoth over billions of years. Each dim glow represents more than just a star. It is a lost galaxy, long since absorbed into the greater whole. The surrounding environment, often called the fiery realm of Abell 2029, is a place of extreme conditions. The intracluster medium, a searing plasma heated to tens of millions of degrees, fills the space between galaxies. This inferno is a direct result of gravitational energy released during galactic interactions, as smaller systems are drawn into the gravitational throne of the cluster's core. Their gas is stripped away, enriching the scorching medium. These processes shape not only the cluster's fate, but also the continued evolution of this cosmic monarch. The story of this interstellar giant unfolds across the entire electromagnetic spectrum. Radio waves reveal vast lobes of relativistic particles, remnants of past outbursts from its central black hole. Infrared surveys uncover traces of dust-silent echoes of an era when star formation was still possible. Every wavelength of light paints a different portrait, offering astronomers a multifaceted view of this infinite expanse of Abell 2029. Yet, the greatest mystery of this silent king of clusters lies in what cannot be seen. Dark matter, the invisible substance that dominates the universe's mass, plays a fundamental role in its structure. Without an immense dark matter halo encasing this stellar leviathan, its gravitational influence could not hold such a sprawling structure. Together, this invisible crown extends well beyond the galaxy's visible boundaries, binding not only its stars, but also anchoring the entire Abell 2029 cluster. The timeless Galaxies is more than just a relic. It is a symbol of the universe's relentless expansion. As space itself stretches, galaxies grow more isolated. One day, far in the future, the Abell 2029 cluster will drift so far from its cosmic neighbors that it will become an island of light in an otherwise unreachable void. The stellar empire will remain, but its surroundings will fade into darkness, a sobering reminder of the inexorable forces shaping the cosmos. Yet, in its present form, the eternal beacon of Virgo continues to shine, offering humanity a glimpse into the ultimate limits of galactic evolution. It stands as both a challenge and an inspiration, a cosmic enigma urging astronomers to push the boundaries of knowledge. Each discovery brings us closer to unraveling the mysteries of this cosmic colossus, deepening our understanding of the largest and most ancient structures in the universe. The primordial sovereign of Abell 2029, sometimes called the cosmic monarch of Virgo, is not merely a passive relic. It is a living record of the universe's history. Every star in its vast expanse, every whisper of gas, and every drifting shadow of dark matter tells a story spanning billions of years. This stellar labyrinth challenges our perceptions of time and space, inviting us to decipher its secrets and reminding us of the infinite complexity of the cosmos. The sheer size of this galactic behemoth, sometimes described as the infinite tapestry of Virgo, places it in a category of its own. Spanning over 6 million light-years, it exists only in the densest and most ancient galactic environments. The Abell 2029 cluster, a gravitational cauldron of thousands of galaxies, provided the perfect conditions for such a titan to emerge. At the heart of this vast system, the cosmic overlord dominates its region, its gravity shaping the motions of galaxies, stars, and gas across an immense scale. For all its grandeur, this celestial titan is not an immortal entity. One day, its stars will fade, its black hole will quiet, and its surroundings will slip beyond the cosmic horizon. But for now, it remains a beacon of knowledge, a monument to the forces that have sculpted the universe. Studying this stellar leviathan continues to challenge and refine our understanding of how galaxies live, evolve, and ultimately face their cosmic fate. The environment of the celestial monarch is one of extremes. The Abell 2029 cluster, a dense conglomeration of galaxies, is suffused with hot plasma that radiates X-rays detectable by telescopes like Chandra. This cosmic furnace is fueled by gas stripped from smaller galaxies as they pass through the cluster, compressed and heated by gravitational forces. These interactions enrich the intracluster medium, creating the high-energy conditions necessary for sustained X-ray emissions. For now, this timeless sentinel stands as a reminder of cosmic grandeur, a testament to the past, a guide to the present, and a vision of the universe's inevitable fate. Despite its eventual fate, the universal titan remains a source of inspiration and discovery, challenging our understanding of the cosmos. Each new observation brings us closer to uncovering not only the nature of this galactic giant, but also the fundamental forces that shape the universe itself. The primordial Colossus, sometimes revered as the king of galactic giants, stands as a monument to the immense creative and destructive forces at play in the cosmos. Its story, spanning billions of years, is a narrative of formation, destruction, and rebirth, a microcosm of the universe's constant flux. This galactic juggernaut embodies both the beauty and the violence of large-scale cosmic evolution, offering an unparalleled laboratory for exploring the mechanics of the universe. At its heart lies a region of unfathomable energy and density, a supermassive black hole, often referred to as the engine of eternity. This gravitational leviathan does more than consume, it transforms. Gas and dust drawn into its event horizon are either devoured or ejected in powerful relativistic jets, traveling near the speed of light. These outflows heat surrounding gas, preventing new stars from forming and shaping the broader structure of the galaxy. This dark monarch at the galaxy's core is both a creator and a destroyer, continuously influencing the evolution of its host. Moving outward from this gravitational abyss, the structure of the galaxy itself stands as a testament to endurance. Sometimes romantically termed the stellar palace, it houses trillions of stars, many of which have long outlived their prime. These ancient suns, dimmed and reddened by time, are relics of a distant epoch when the galaxy teemed with star-forming activity. Today, their soft radiance gives the celestial elder its characteristic golden hue, a reminder of its advanced stage of evolution. Beyond this warm glow, an even more elusive component, dark matter, the silent architect of the cosmos. This unseen force envelops the galaxy, providing the gravitational cohesion necessary to maintain its vast structure. The dark halo surrounding the stellar leviathan extends millions of light years beyond its luminous core, not only holding the galaxy together, but also influencing the entire Abell 2029 cluster.